Hello students, we'll be reviewing the 2020 H3 paper. It will be reviewed in sequence from question 1 all the way to question 8. It is done in the hopes that it will be useful for your revision towards your upcoming H3 exams. Okay, for the first question, which is a stimulus-based question, the stimulus is given in the inserts. So it's a separate piece of information. And you can take note of some of the information, and I'm going to run you through some of the important details you might want to pay attention to. Okay, it is clear that from the stimulus given, everything is on electrochem. The concepts which they want to test you for this particular stimulus is largely on electrochem, and I think it's written here that it's a vanadium redox flow cell. The first part of the abstract gives you a summary of the findings by the scientist. Okay, this is a vanadium redox flow cell. You have a combination of vanadium 2, vanadium 3, as well as vanadium 4 and vanadium 5 as the redox couples for the negative and positive electrode respectively. Yeah, if you wish to, you can just take note of it by putting a minus here and a plus here. Yeah, but if you don't wish to, it's perfectly fine. It doesn't really matter, because along the way, from the information given, I think it will be plain what is the purpose of the relevant half cells, and what do they do? Is it an anode or cathode? Yeah. In case you are very scared here and you're not sure, oh, is it a cathode or anode whatsoever, right? I think it doesn't really matter at this stage. Of course, if you are aware of it, then it's better. But if it's not, it's fine. There will be ample clues and information given to you along the way. Then you were told that you have 1.5 moles per Dn of vanadium ions solutions in sulfuric acid. It's being kept at pH 0, so it's particularly acidic. Yeah, so this might be an important point for you to take note of later on, because I think in the last part of the question they require to do some evaluation. Okay, other than that, I think it's just information for you. And then you were told that there's a polystyrene sulfonic acid cation selective membrane. Might be crucial for you to know that this is a cation selective membrane. So that means that it allows certain cations to pass through. And then the cell was charged, okay, at 40 milliamperes per square centimeters, and then discharged across various loads. This might be the two most important terms that's often misunderstood by students. So I thought we want to take this or use this opportunity to explain to the students. I think in everyday language, we are very clear what the meaning of charging is. Okay, so for example, if your laptop battery or your handphone battery runs out, you start out with 100% battery, and then it goes all the way to, let's say, 5% or even 1% or even 0%, right? Then normally you will tell people that, oh, I need to charge my phone. So what do you do when you want to charge your phone? You plug it into an external power supply on the power plug, and then after that it will charge on its own. So we all understand what's the meaning of charging, but chemically, do we understand what's the meaning of charging? Yeah, so actually charging, right, is to reverse the process. Okay, when you're using your mobile phone, there's a chemical reaction going on in your mobile phone battery which allows electrons to be driven through the circuit, so-called, in the simplistic sense. Yeah, however, it only goes in one direction. So eventually, when all the starting material has been used up, then that's where your handphone battery goes flat. And you need to charge it in order to allow the reverse non-spontaneous process to take place. Yeah, so that is where you either plug it into the external power supply, or you plug it into a power bank, something along those lines. Yeah, so basically charging is to allow the reverse non-spontaneous reaction to take place. And then what about the forward reaction? In everyday language, we don't talk about the forward reaction. We just say that we use our laptop with the battery. We use our mobile phones with the battery. Yeah. So actually, when we're using it without plugging into the external power supply, this is called discharging. So you say that your battery discharges, okay, as you are using a mobile phone or as you are using a laptop. Yeah, so I think you need to get these two terms correctly defined, or you need to understand these two terms before you move on to do other things and answer the questions. Okay, so after that, you were told that the Coulombic efficiency was 90%, while the voltage efficiency calculated over the 10 to 90% state of charge was 81%. So these are just some details, some numbers given to you. And then later on, you were told that overall energy efficiency for the cell was 73%, together with the simplicity of the system makes the vanadium redox cell one of the most promising energy storage, etc., etc., etc. Okay, now so if you take a look at this particular setup, right, you will notice that it resembles or it should resembles the one given to you in the first paragraph. So vanadium 2, vanadium 3 is what we call the negative half cell, and vanadium 4, vanadium 5 is what we call the positive half cell. Okay, and then after that they are being connected to the external circuit. Okay, so it is clear that this is an electrochemical cell. Okay, so let me repeat. It must be clear that this is a electrochemical cell. Okay, and then what exactly are the processes taking place in this particular system? Okay, that is the question that is being asked of you later on. I mean, if you wish to, you can also go to the data booklet over here to look at some of the information given to you regarding the vanadium 2, and then vanadium 4, vanadium 5. Then I think from there you can sort of decide what exactly is the reaction taking place. I mean, if you wish to do that now, you can. Okay, so maybe let's try to do that. So you have a vanadium 3. Okay, so let us just take the relevant information. So we have vanadium 2, vanadium 3, and then over here you have vanadium 4, vanadium 5. So this is vanadium 4, vanadium 5 in acidic medium. It's over here. So vanadium 4, vanadium 5. Okay, so therefore you can easily actually calculate the E cell over here. So E cell is essentially E reduction minus E oxidation. So that would be vanadium 5, vanadium 4, minus vanadium 3, vanadium 2. Okay, so this would be equals to 1.00 minus 0.26. So this is plus 1.26 volts. Yeah, so even before you start doing the question, you will be able to tell that based on the setup given to us, okay, the cathodes is actually the vanadium 4, vanadium 5 half cell. So vanadium 4, vanadium 5 half cell, so this is the cathodes. Okay, and then the anodes is over here. Okay, and then if you can recall what happens at the anodes. Okay, so the anodes is when oxidation takes place. So vanadium 2 gets oxidized to vanadium 3 and in the process generates electrons. So that's why it's the negative half cell. And then for the reduction, vanadium 5 is consuming electrons from the circuit. So in this case, it's being reduced to vanadium 4. Okay, so everything fits the description, it fits the information given to us in the data booklet. Yeah, so this is one of the exam strategies you might want to employ when you do the question. Like pick up relevant information and then write in the relevant points in your, I mean, the inserts is actually the stimulus, right? So you can actually write information there. So as and when you wish to, just write information down so that you become a little bit more confident of approaching the questions. You will not stumble. Okay, I think these are some of the exam techniques you need to pick up. Okay, so yeah, so let's read on. And then you were told that the half cell for each of the membrane needs only a small proportion of total electrolyte volume. So these are some details. So as the cell discharges or charges, I can then pump in fresh electrolyte, and then so that over time all the electrolyte used. And then later on, they give you some interesting information such as this. The carbon sheets show not to degrade even after 10,000 charge discharge cycles. Okay, and then many cells can join in series to provide the required voltage. Those of you doing physics, or if you remember the physics you learned in secondary school, you understand what this information means. Okay, and then moving on to abstract 2, and then you notice that's actually the end. It's written that initially both sides of the cells are filled with 1.5 moles per liter cube solution of VOSO4. If this formula seems a bit daunting, you can actually just write it as VO2 plus and then SO4 2 minus. And then in that case, your vanadium is actually vanadium 4. Okay, and then the potential difference is applied across the cell, and then okay, so this is charging in some sense. So we actually started with vanadium 4, and then when we apply a potential difference, right, vanadium 4 will be reduced to vanadium 2. This is written over here. Vanadium 4 is reduced to vanadium 2, and then vanadium 4 will then at the right side will then be oxidized to vanadium 5. Why is there a need to generate vanadium 2 and vanadium 5 in that sense? Well, I mean, as we explained earlier on, in order for the battery to work, vanadium 5 must be reduced to vanadium 4 and then vanadium 2 oxidized to vanadium 3, and then you get a voltage of 1.26. Yeah, so that's the idea which they want to present to you. And then this is an interesting paragraph. You were told that twice as many coulombs are required to produce the electrolyte in the negative half cell as compared to those required to produce the electrolyte in the positive half cell. In case you are wondering why, right? I don't think this is any complicated, because when you go from vanadium 4 to vanadium 2, that is actually you will actually take in 2 electrons, right? And then when the positive half cell gets oxidized from vanadium 4 to vanadium 5, you actually just take in 1 equivalent mole of electrons. Yeah, so it wouldn't come as a surprise why is it that twice as many coulombs are required. Okay, so I thought that information is given to you just to reinforce some of your understanding in case you missed out some of the details. And then if the positive half cell is overcharged, oxygen is produced. In that case, that means that you are actually allowing the oxidation of water, I guess. Yeah, in order to produce oxygen. Yeah, so you cannot overcharge it. So this is important. So in order to avoid this, they will actually use twice the volume of electrolyte in the positive half cell during the initial charging. So this is actually to prevent but I mean, in your positive half cell, your vanadium 4 will be oxidized to vanadium 5. But if there's not enough vanadium 4, then water will be oxidized instead. So in order to prevent that, they will actually use double the volume. So that's the idea that they want to impress upon you. Then after that, after complete charging, additional electrolyte is removed, leaving equal volume on each side. Yeah, so I think these are some of the information provided for you to read through. I hope this explanation will allow you to see through the fog and then maybe make the understanding of this stimulus easier. Okay, and then after that, we'll move on to the actual question. You notice that the actual question is actually very H2-ish. It's not very tough, but you need to think a lot. Yeah, so there are a lot of ideas you need to think through before you even come up with a possible answer. So, okay, so let's look at A part 1. For A part 1, you are asked to write a balance equation to show the production of vanadium 2 and vanadium 5 from vanadium 4 at the start of the experiment. Okay, so I mean this wouldn't be very difficult. So therefore, we are looking at the cathodes here. Okay, so the cathode, you can well, I mean there are a few ways you can do it. You can just copy. Oh, sorry, you can just copy the information, or you can just derive it on your own. But of course, copying from a data booklet is definitely a lot easier. So we have VO vanadium 4 plus 2 electrons plus 2H plus, and then in the process I get vanadium 2 plus H2O. State symbols is not required, so I think you don't have to write in. If you want to write in, you can, but just remember that water is liquid, not aqueous. That's a very common mistake students will make. So charging your anode, so your vanadium 4 will be oxidized to vanadium 5. Okay, so remember that when you are writing, right, please make sure that you are writing the process that is taking place. Okay, because this is what the question asks of you. you are not writing you're not writing them in terms of the half equation given your data booklet. You are writing the process that leads to the production of vanadium 2 and vanadium 5. So make sure that you write them properly and your electrons appear in the correct place, and make sure that you are using a full arrow to describe your reaction. If not, then what you have written will not serve any purpose. Okay, after that they wrote hence explain why twice the volume of electrolytes is used in the positive half cell. I think we have already explained earlier on. Okay, so you realize from here that for every one equivalent of vanadium 2 that is formed, right, where it will consume 2 equivalent of electrons by vanadium 4, you will actually need 2 equivalent of vanadium 5 to be produced. Yeah, because the production of vanadium 5 will provide that electrons which will then be used to balance or used to reduce vanadium 4 to vanadium 2. So in order to balance both sides, right, therefore you actually need you actually need to realize that for the anode you need twice the amount of vanadium 4 in order for you to generate the right amount of electrons so that on the other side your cathode can then have the stoichiometric amount of vanadium 4 being reduced to vanadium 2. Okay, yeah, and then of course if there isn't enough at the anode, then you are going to run into the issue of water being oxidized to oxygen. So that is a very real problem which was being addressed to you in the question. Okay, after that for part 2, right, you are asked to write a half equation to show how oxygen would be produced if overcharging were to occur, right? So I think I also mentioned verbally earlier on, if overcharging were to occur, what will happen? It will result in the oxidation of water to give oxygen gas. In this case, 4 electrons being transferred. Okay, so this is not something we want to take place. Okay. Next, we'll move on to part B. Okay, you were told that during discharge, electrons travel around the circuit and ions migrate through the cell's cation selective membrane. Use data from data booklet to calculate E cell. Okay, I have already done that over here. Okay, so this will be the answer. Okay, to B part 1. Okay, so E reduction minus E oxidation. So when this particular battery, the vanadium flow cell battery, operates, vanadium 5 will be reduced to vanadium 4, and then vanadium 2 will be oxidized to vanadium 3, and then the voltage generated will be 1.26 volts. Okay, then after that, B part 2, you are asked to deduce the identity of the ions that migrate through the cation selective membrane and states the direction of travel. Okay, so this is quite interesting. So let us take a look at this. Okay, I hope that you can see from here. It might be easier. Hopefully. Okay, so now first of all, right, when vanadium 5 gets reduced to vanadium 4, you notice that H plus is being consumed. Okay, so vanadium 5 reduced to vanadium 4. So this is the cathodes. Okay, and then vanadium 2 gets oxidized to vanadium 3. So this is the anodes. Okay, so you notice that at the cathode site, right, as the reduction proceeds, the total positive charge actually reduces from +3 to +2. Yeah, so I hope you notice this as the reaction proceeds. So as the reaction proceeds, your cathode become increasingly less positive, and then your anode become increasingly more positive, right? Because it goes from vanadium 2 to vanadium 3. So eventually there will be an imbalance of charge, right? Agree? Where your cathode become increasingly less positive, your anode become increasingly more positive. Yeah, so this imbalance eventually might cause a short circuit. So therefore, you need your cation selective membrane, right, in order for your H plus to migrate from the anodes to the cathodes. okay, in order to balance off the charge. So it's kind of like a salt bridge, but you don't call that a salt bridge. Yeah, but it serves the same purpose as the salt bridge. And of course, the main purpose is to maintain electrical neutrality on both sides. I mean, that's a very kind of standard H2 kind of answers that people normally will give. Yeah. Okay. So in short, I think if you want to draft an answer out for a 1 mark question, you can write it in a very simple way. You can just say that at the cathode, as a reaction proceeds, the cathode becomes increasingly less positive, the anode becomes increasingly more positive. Yeah. So in order to maintain electrical neutrality, H plus needs to migrates from the anodes to the cathodes. Yeah, so as to maintain electrical neutrality lah, or as to balance the positive charge. Okay, so to answer the question is not very difficult, but it's a thought process lah. So I think you need to be able to be crystal clear about what exactly is going on when you attempt the question. Okay, then we'll move on to the next part where you're supposed to apply some mathematics to solve the problem. Okay, so you were told that when the concentration of the ions in the electrolyte are not 1 mole per dm cube, you can actually scale it by using equation 1.1. Okay, so you were told that the potential of a half cell can be calculated. So this is the one under standard condition. And then you scale it using this particular factor. And then you will it's being defined what are these things. So N is the number of electrons transferred during the electrode reaction, and then the concentration of oxidized species and the concentration of the reduced species. Okay, yeah. So basically, given that equation, given the number of moles of electron transfer, given the concentration, when you plug everything together, you can actually account for the new potential of the half cell. And then for part 3, you are supposed to use equation 1.1 to calculate the potential of each half cell. Yeah, so this is actually crucial. Potential of each half cell. So both cathode and anode, like very important. You are not just calculating for one. Okay, let me repeat. You're not just calculating for one. You are calculating both you are using this correction factor. Okay, this is the correction factor. You are using this correction factor, right, to determine the E cathode and the E anode, and then eventually determine the cell potential. Okay, what is the condition given to you? This is the condition given to us when the cell is 90% charged. So you're supposed to show your working clearly because it's not a very straightforward question. Okay, what is the meaning when we say that the cell is 90% charged? I think that is a very important question we need to come to terms with, we need to understand before we even continue working on the problem. Okay, so let's say we want to calculate E cathodes. Okay, we want to calculate E cathodes. So this is actually the reduction half cell. Yeah, then what is the reduction half cell we are talking about? We are talking about vanadium 5 and vanadium 4, right? So this is vanadium 5, this is vanadium 4. Okay, now so the standard reduction potential of vanadium 5, vanadium 4 is 1.00. And then we will factor this in. Let me just write it in first before we explain further. Let me just write it in first. 592. 1 electron is being transferred. Okay, so 1 electron is being transferred. Yep. Okay, then 1 over here. And I need to lock it. Okay, now what is the ratio of the oxidized to the reduced species? That is very important. Okay, so 90% charge here means that I will have 90% of vanadium 5 because that is the species with a higher oxidation state. Okay, and vanadium 4 is the one with the lower oxidation state. So in this case, the ratio will be 0.9 is to 0.1. Okay, so we'll factor this in, and then you punch the calculator, you will be able to get 1.056 5 volts. Okay, so we'll do the same thing for the E anodes. E anodes over here. So for E anodes, we are looking at vanadium 3, vanadium 2. So again, one electron is being transferred. So that is minus 0.26. Then we do the same factoring, 0.0592 divided by 1, and then log. Okay, so again, 90% charged. So it's the other way around because I will have 10% of the oxidized species and 90% of the reduced species, right? So in this case, my reduced species is vanadium 2, my oxidized species is vanadium 1. So again, the ratio is 0.1 divided by 0. Okay, so you have to be very clear about what exactly is going on here. And then from here, you will get minus 0.3165 volts. Okay, then based on these two, you can calculate E cell. So E cell will then be E reduction minus E oxidation. So that's 1.0565 minus minus 0.03165. Sorry, 0.3165. Okay, then I will be able to get plus 1.37 volts. Okay, so just make sure that you understand the language very clearly. If you still have some issues trying to understand this, I think it will be good to go back and think about it and then reflect on the information given to you. Okay, or you can pause the video for a while and then after that move on. Okay, so next we move on to part 4. So part 4 reads, as the cell discharges, the potential drops. So now they ask you to use equation 1.1 to calculate the total cell potential when the cell is 90% discharged. So actually, you are doing the same calculation. I don't know whether you agree with me or not. You're going to do the same calculation. So what do I mean by doing the same calculation? You are just calculating the E cathode again based on the 90% discharged. Okay, so that's 1.00 plus 0.0592 divided by 1 log the other way around 0.1 divided by 0.8. Okay, and then I will be able to get plus 0.9435 volts, and then I'm going to do the same thing. E anodes is equals to minus 0.26 plus 0.0592 over 1, and then log the other way around 0.9 over 0.1. Okay, and then I will be able to get minus 0.2035 volts. So with this, I will be able to get the new E cell. So this is the new E cell, and then I will calculate to be 0.9435 minus 0.035, and then I will be able to get 1 plus 1.147 volts or plus 1.15 volts. Okay, can? Then after that, you are asked to calculate the drop in overall cell potential when the state of the cell changes from 90% charged to 90% discharged. Okay, so from here I will be able to calculate the drop in overall cell potential. Okay, is equals to 1.373 minus 1.147. Then I will get 0.226 volts. You realize that this question actually made you realize that as you go about using your mobile phone batteries or laptop batteries, right? Actually, the cell potential drops over time. Yeah, so that's something that I think many of us in our everyday life we might not realize. Yeah, but I think it's good to be clear about it. And I hope that when you are attempting this question, right, you learn something from it as well. Okay, next we'll move on to C part 1. Okay, so C part 1 reads, assume that the total vanadium concentration remains as 1.5 moles per dmq in each half cell, and each half cell contains 1 dmq of solution. Calculate the total charge in coulombs that would travel around the circuit, external circuit, sorry, when the state of the cell changes from 90% charged to 90% discharged. Okay, so from here, I think we will need to look at the total number of moles of electrons being transferred. Okay, so I think from here we can calculate the number of moles of electron flow, number of moles of electron flow. Okay, so each of the half cell is 1.5 moles per ln cube, right? You realize that the electron transfer for each of them is 1. Yeah, so if you have 1.5 moles per ln cube, so that will be 1.5. Okay, going for 90% charge. Okay, to 90% discharge. Okay, so that will be this 0.1, and then we'll end up with 1.2 moles, 1.2 moles of electrons. Okay, so in that case, the total charge, okay, will be equals to this total charge is actually per mole of electrolyte, of course. Okay, so it's actually number of moles of electrons multiplied by Faraday. So that gives 1.2 96500. So that will be 1.16 times 10 to the power of 5 coulombs. Okay, so C part 1 seems difficult, but it's actually a very straightforward calculation, which is 1 mark, because there's only one step. Essentially, it's only one step. You just need to realize that there is a difference of 80% occurring because you are going from 90% charged to 90% discharged. Okay, so for the charge species, to reduce 80% over in the course of the reaction. Okay, so next we have equation 1.2 shows how the energy produced by a cell is related to the potential and the charge and the charged past. After that, you are supposed to use equation 1.2 and your answer to C part 1, right, to calculate the energy given out by the cell during the change from 90% charged to 90% discharge. Okay, so use the E cell you have calculated in B1. Okay, so the E cell are calculated in B1. I think it's the one, yeah, this is the one. So it's 1.26 volts. Okay, so that will be energy given out. Energy given out is actually equals to 1.26 multiplied by the above, which is 1.16 times 10 to the power of 5. Yeah, so I'm going to end up with 146 kilojoules of energy. Okay, I'm solely using the information given to me. So it's here, potential and charge. So the charge I've calculated is based on this. So I just sub it in here and then I'll get 146 kilojoules. Okay, then for part 3, you were told that a small town might use 36,000 megajoules of electrical energy per day. Calculate the volume of the electrolyte that will need to be passed from the storage tanks through each half cell to provide this energy. And then you are told to assume 100% efficiency, and then the cell changes from 90% charge to 90% discharge. So this is quite interesting as well. And then you were told that 1 megajoule is equals to 1 times 10 to the power of 6 joules. Okay, so in that case, we'll just do the calculation directly because we can simply use the answer to part 2. So therefore, the volume of electrolytes needed, okay, is therefore equals to 36,000, okay, multiplied by 10 to the power of 6, divide by 146 times 10 to the power of 3. Okay, so from here, I will be able to get the volume of electrolyte required. That would be, let me just punch the calculator, I'll get 247 times 10 to the power of 3 dn cube. Okay, and then of course I can just convert it and I will get 247 cubic meter. Okay, can I hope everything's going on okay, and you understand the ideas. Okay, yep. in case you're wondering why divide, right? Because earlier on, when we had 1 dm cube of the solution in each of the half cell, this is the amount of energy we produce. Yeah, so in order for me to obtain the electrolyte I need in terms of dm cube, then I will just divide it directly, because whatever information I have over here, if you wish to, you can write that down. Whatever information I have here, right, this is actually per 1 dm cube of electrolyte. If you wish to write down, this is actually per 1 dm cube of electrolyte. Yeah. Then this is also this total charge transfer. This is also per 1 dm cube electrolyte. So if you indicated this clearly, right, then you will understand why over here, right, I need to divide them in order to get a total volume of electrolyte which I require. Okay. Yeah. Then finally, for part 4, remember earlier on in the insert, I was telling you some of the things like highly acidic, and then later on I mentioned here that the carbon sheets, all this will not degrade over time. Yeah, so this will form part of your answer to part 4, because part 4 actually asks you to discuss the advantages and disadvantages of using the vanadium redox flow cell as an energy storage medium. Okay, so because earlier on I already highlighted the acidic part, maybe I can talk about the disadvantages first. Okay, so of course for the disadvantages, I'm using very strong acid which might cause harm to the environment if accidental leakage were to occur. Okay, then you also realize you are using a transition metal, in this case vanadium, which could be rare. Okay, so at that point in time when you're doing the question, you're not sure, but usually vanadium, or rather usually transition metals are quite rare and probably expensive. And of course toxic as well. So these are some of the things you could mention regarding transition metals to be used. Okay, so they are usually toxic, rare, expensive. Okay, things you can mention as part of the answer. Then of course the advantages, I think I'm not sure whether you can recognize the very beautiful chemistry here. For the initial stage, right, when I'm charging up the system, I actually only need to use one reactant, which is vanadium 4. Yeah, so I only need one source, so I don't need to go and source for different reactants put together. So I only need one source. So this actually adds convenience to the system. I mean for my setting out of the experiments. Okay, and then of course you notice that your electrolyte is often utilized again, so replenished, and you can charge and discharge. Of course, over time, maybe some of you degrade, but that wasn't exactly mentioned. So that is also something which you can mention in your answer. So there's no wastage of the electrolytes. Okay, and of course, the most important part is actually given here. Your carbon sheets, the electrodes are shown not to degrade over time. I mean, 10,000 charge discharge cycles, it will still be there. So actually, it's not too shabby. Yeah, so it will still be around after quite a long time. So yeah, so your electrodes, I mean, it can withstand the strong acid and to be able to charge and discharge without degrading. So in that case, this is one of the advantage we can think about for this particular vanadium flow battery. Okay, so that will be the end of question 1. I hope you find it useful, and if you have further questions, do feel free to write it down in the comments below.
Okay, the next question we are going to look at is question 2. Okay, you have seen from figure 2.1 that you are expecting molecular orbital theory. Okay, so you are told that the atomic orbitals of electronegative atoms are lower in energy than those of less electronegative ones. Okay, so if you look at the diagram being drawn for you, atom A has the same electronegativity, so this is usually the homodiatomics which you have encountered in your drawing of MO. I think within your curriculum, you should be able to draw molecules such as nitrogen, oxygen, and fluorine, and even neon. Okay, so the normal hormonal diatomics, which you are familiar with, have the atomic orbitals at the same level. Okay, so for this particular question, you were told that atom B being more electronegative than atom A, right, will actually be of a lower electronic energy level. Yeah, so they deliberately give you this information because if you look at part A, they would like you to draw nitrogen, oxygen, as well as NO. So for N and O, oxygen is more electronegative, so you expect oxygen to be lower than nitrogen. Yeah, something along those lines. Yeah, but before that, let us try to draw the molecular orbital diagrams for nitrogen gas. Okay, so for nitrogen gas, what we are expecting would be maybe before we start to draw, we can state the electronic configuration for nitrogen. So for nitrogen, you are expecting 1s2, 2s2, 2p3. Okay, so for oxygen would be 1s2, 2s2, 2p4. Okay, so therefore in the case of nitrogen, we expect maybe 1s over here. So this is in terms of energy. So maybe let me just erase this. I think we need a little bit more space. Okay, so we have energy. Okay, axis, and so over here we have 1s. Okay, so we have 1s and then 1s. So 1s will be filled with electrons on both sides. Okay, so we're going to end up with something like this. Okay, then after that we'll be looking at 2s. So 2s will be here, 2s will be here. So we're going to paint the same narrative. So we're going to have something like this, 2s. Okay, then right now we're going to have 3p, so we're going to have 2p, so we're going to have 2p over here, so 2p. So for nitrogen, you have single electrons, like this. Okay, then sigma bond formation, because they assume no orbital mixing, so sigma bond formation will be of a lower electronic energy level, so it will be here, and then after that followed by pi bond formation, so that's 1, 2, 3, 4. Okay, then you have something like this. Okay, so this is the kind of MO diagrams we are expecting. Yeah, so if we want to label it, then this would be, maybe I'll just change the color for labeling, so I'll change to purple. So this will be sigma 1s, sigma 1s star, so that's anti-bonding sigma star. So this is sigma 2s, sigma 2s anti-bonding. Okay, so this will be sigma 2p, these two will be pi 2p, so one will be px, the other will be py. Okay, so this is pi 2p anti-bonding, this is sigma 2p anti-bonding. Okay, so this will be the molecular orbital diagram for nitrogen. Okay, so I just put it here. I will not repeat for the drawing of oxygen because it will it will look almost the same, except that for oxygen you have one extra electrons in the 2p orbital, so I'm just going to write in red, and then after that you're going to have two unpaired electrons over here. Okay, so the one in red here will be the molecular orbital, the MO diagram for dioxygen. Okay, O2. Yep. Okay, so you will have to draw the full one, not like me just erased. Okay, so for illustrative purposes, I'm just going to erase it so that you don't have to spend too much time listening to me drawing the whole thing again. Okay, then the next thing we're going to look at is we're going to look at NO. Yeah. So NO, you are explicitly told that oxygen will be of a lower electronic energy level. So let us just try to draw it. Okay, so I'm just going to level the energy for nitrogen first. So nitrogen will be on the left. So this will be nitrogen. So this will be, I will start with 1s. Okay, and then I'll have a 2s somewhere higher. Okay, maybe I should draw it a lot higher so that there are space. Okay, so this is 2s. And then I'm going to have 2p here. So because it's nitrogen, I'm just going to fill with electrons, 1, 2, 3. 4, 5, 6, 7. Okay, then I'm going to use green to represent oxygen. So oxygen will be lower, so it will be here. So that will be 1s for oxygen, and then this will be 2s for oxygen. Okay, then I'm going to input 2p for oxygen as well. Okay, but not to forget, oxygen has an extra electrons at the 2p. Okay, so right now I'm just going to link up everything. So it will be something like this. My apologies if it's not really drawn in scale. Yeah, because of my poor drawing. So yeah. Okay, so yeah, okay. Okay, I think I should just lower this portion so that everything will look nicer. Okay, so I'm just going to lower this part. Yeah, I'm just going to lower the 1s over here. So 1s, and then this will be the 1s. Okay, so I'm just going to lower it so that it will make a lot more sense. Yep. Okay. So electrons, then so electrons. Okay. Then I will shift this higher so that the drawing will look nicer. Okay. So I'm going to put the 2p here. Okay, and then the 2p for oxygen. Okay. Yeah, I think I need to shift it so that it doesn't overlap unnecessarily. Okay. Okay, so 2p. Okay, yeah. So right now I'm just going to link them up. So this will be the sigma, and then this is the pi. 1, 2. So we have 7 in total. So there are 1, 2, 3, 4, 5, 6, and then we have 7. Okay, so this will be the diagram which we are going to expect. Okay, so my apologies that it doesn't look very nice, but yeah, you get the idea if you just space them out nicely. Okay, so if you're going to label now, I'm going to write orange. So this will be sigma 1s, sigma 1s anti-bonding, sigma 2s, sigma 2s anti-bonding, sigma 2p, pi 2p, and then this is pi 2p anti-bonding. This will be sigma 2p anti-bonding. Okay, so let's just check whether we are done with everything. So we have successfully drawn the MO diagram for N2 and O2, although I just combine them in the same diagram just for illustrative purposes in this particular review video, and then NO, and then in each case populate the orbitals with the appropriate number of electrons. So we have done that. Assume no orbital mixing, we have done that as well. Okay, yeah, pretty much we're done for this. Maybe before we move on, it might be good for us to calculate the bond order. Okay, so this is to help us keep track of the change in the bond strength in the course of filling up or populating the MO with electrons. Okay, so I think it will be good for us to determine the bond order of N2, the bond order of O2, and the bond order of NO. Okay, so earlier on you have seen that the bond order of N2 is actually those the blue electrons, with the blue representation of the electrons. Okay, so to calculate it, we just sum up the total number of electrons in the bonding from the total number of electrons in the anti-bonding MOs. Okay, so in that case, the bond order of nitrogen will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that will be 10, okay, minus 2, 4. Okay, and that's it, just minus 4. So I'm going to divide by 2. So I'm going to get bond order of 3 for the bond order of F2. Okay, then for oxygen, you realize that there are 2 extra electrons in the anti-bonding. I've circled over here. So therefore, for oxygen, it will be 10 minus 6 divided by 2. So this will be 2. Okay, and for NO, it will be quite interesting. The total number of electrons will be 2, 4, 5, 6, 7, 8, 9, 10. Okay, so let us just try again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 will be 10 electrons. Did we do something wrong over here? So let me just double confirm. Is it really 10 electrons? 2, 4, 6, 8, 10. Yeah, it's correct. It's 10 electrons. So 10 electrons in the bonding, and then anti-bonding will be 2, 4, 5. So minus 5. Okay, so that's right, because the total number of electrons, yes, is correct. Because we are looking at 7 plus 8, yeah, so that's 15, correct. Okay, so divide by 2. So we get bond order of 2.5. Wow. Okay, so 2.5 for NO, O2 will be bond order 2, N2 will be 3. Okay, so with that knowledge, maybe I can just write down here the bond order. This is 3, 2, and 2.5. Okay, we have a question over here to ask us to comment on the relative values of these properties with reference to the diagram drawn in part A. Okay, so I think in order to answer this question, the first thing you might want to highlight to the examiner is that the bond order of N2, O2, and NO is calculated to be 3, 2, and 2.5 respectively. It is important to highlight this before you jump into answering the question. For a relatively simple reason, because the three physical properties listed here are bond energy, which is intimately related to the bond order. So you realize that NN triple bond has a bond energy of 944, it has a bond order of 3, and NO double bond has a bond order of 2.5 and bond energy of 626. Oxygen, also a double bond, but it has a much lower bond energy of 496 and is shown to have a bond order of 2. So in that case, you should be able to conclude that the bond order is a proxy to the bond energy or the bond strength. Okay, so we have kind of covered the bond energy aspect. Remember that bond energy is the amount of energy you need to homolytically cleave in this case the diatomics into their respective gaseous atoms. Okay, and it is not difficult to understand why NO has a stronger bond energy than O2 without going to NO. Yeah, because NO is a polar covalent bond. Yeah, so it is strengthened by the partial ionic character. Yeah, but if you know a little bit more about NO, you realize that the strengthening of the partial ionic character has a lot to do with the fact that because the molecular orbital of the bonding orbitals are actually lower in electronic energy, and this actually gives rise to a stronger interaction between the electrons and the nucleus. Okay, in that sense. Yeah. So with that, from the bond order, you can use it as a proxy to explain why the bond energy is in this particular order. And you can also use it to explain the bond length, because the stronger the strength of the covalent bond, the shorter the bond length. So you can see that N2, having the strongest NN covalent bonds, it has the shortest bond length of 0.10 nanometers, followed by NO, and then followed by oxygen. Okay, so I'm sure you can see this. Okay, however, ionization energy might be the part where it gets a little bit difficult to explain, because you realize that NO, right, has the lowest first IE, despite the fact that its bond order is relatively high in between the two. Okay, but for IE, right, you cannot explain using bond order directly. Okay, the reason is if you take note of the formula of the bond order, right? It is the total number of electrons in the bonding molecular orbitals subtracting away the total number of electrons in the anti-bonding molecular orbital. Okay, so you realize that for NO, right, there is one electrons in the pi anti-bonding molecular orbital, and if that is being removed, right, the NO bond will be strengthened further. So that gives that electron so-called an incentive to be removed, because removing it results in the strengthening of the NO bond. Yeah, so this could be the reason why NO has the lowest first IE. Then what about the difference between oxygen and nitrogen? Well, I mean, the difference between oxygen and nitrogen is that you notice that for oxygen, again, the electrons to be removed is actually found in the anti-bonding pi orbital of oxygen. So if I remove that, that also results in the strengthening of the OO covalent bonds. Okay, so there is some logic when it comes to the facts that when I remove electrons from anti-bonding pi star, in our case here it's pi star, it will result in the strengthening of the bond, and this kind of like adds to an incentive in it being removed. Okay, and some of you might be wondering, then in that case, how come the first IE of O2 is higher than that of NO? I mean, in this case, it doesn't really quite make sense, right? Well, I mean, of course, one of the reasons which you probably will not encounter over here, and you are probably not required to explain, is that the 2 pi star, or rather the pi star orbital in NO, right, is actually of a relatively high electronic energy level. It cannot be shown directly in the MO hydrula because of the electronegativity difference, right? This pi star electron, right, is this particular electrons in a pi star orbital, right, is actually closer to nitrogen as compared to these two particular pi star, which is closer to oxygen. Yeah, and of course we know that nitrogen being less electronegative than oxygen, right, will hold onto its electrons less dearly. Yeah, so you can actually bring in some of these facts you have learned in chemical bonding to help you explain that, and that will actually complete the answer as to why NO has a lower first IE than O2, and then why O2 have or why N2 has the highest first IE. Yeah, N2 having the highest first IE, I don't think it needs any explanation, because you're removing electrons from the pi orbital, from the pi molecular orbital, which obviously requires a significant amount of energy, because once it's being removed, right, then the bond order will actually decrease. Yeah, and then another reason which you can think of is that removing electrons from the pi molecular orbital actually requires quite a bit of energy, because the electrons are found deep inside the MO. Yeah, as compared to removing electrons from the anti-bonding molecular orbitals. Okay, then if we move on to the last part where you are asked to suggest with reasons how the bond energy and bond length might change when the NO plus is formed. I think we have already addressed that. So the bond energy will be strengthened, so the NO covalent bond will be stronger, because now the bond order decreases from, or rather increases from 2.5 to 3, and then the bond length will be shortened. Okay, so a shorter and a stronger NO double bond in NO plus. And at the same time, it will lead to an increase in bond order from 2.5 to 3. Okay, so yeah, that's the end of question 2. Okay, next we are going to look at question 3. So for question 3, you were given 2-bromo-2-methyl butane reacting with sodium ethoxide in ethanol to give 2 alkenes. Okay, so in short, we can try to draw this 2-bromo-2-methyl butane. So you have butane structure, 2-methyl over here, and then a bromine. So basically, it's a tertiary halogenal alkanes. Okay, so you were told that under the condition of this reaction, both E1 and E2 mechanism occurs at the same time. You're asked to draw the mechanism for E1 and E2 that produces alkenes A and B. Yeah, so we can easily draw both E1 and E2 out. Okay, so we have a delta plus, delta minus. So we'll just draw it in E1 first. Okay, so this is E1. So we'll draw E1, and then we're going to get a tertiary carbocation. Okay, so once we get the tertiary carbocation, the protons will be removed. So, So if we remove this particular protons using sodium ethoxide, okay, and then we'll end up with A. Okay, if we get it from the other protons. Okay, so with sodium ethoxide as the base, so then we'll end up with B. This is B. Okay, and then the next one will be A. Okay. Right. Okay, my apologies. Actually, the question only requires us to draw to give A. Yeah, so I guess we could ignore this portion. Yeah, so this shouldn't be part of your answers if you're answering the question. But of course, for enrichment purposes, if you want to draw in everything, you could. Okay, then after that, we're going to draw for E2. Okay, so for E2, you're going to have Br over here. So the H. And then sodium ethoxide, so O minus, like this. So we grab the protons, form the pi bond, and then kick out the bromides. Okay, so plus Br minus plus ethoxide. Remember to balance your equation, okay? Because most of the students, they don't end up balancing the equation, and this actually created some problem. Whether Cambridge will deduct marks, that's something else. Okay, so this is E2. Okay, yep. And then explain with reference to your mechanism in A, right? Why the equation for the overall rate of this reaction is given as such. Okay, so I think we need to break it down. If it's solely E1, then we are looking at the rate equals to K1. Dependent on the substrate, which is C5H11 Br. Okay. If it is E2, right, then we are actually looking at the rates dependent on both the substrates. 11 Br. Both the substrates and sodium ethoxide. So that will be NaOEt. Yeah, but in this particular experiment, what we are measuring is actually the overall rate. Yeah, so in that case, we have to sum these two up together. So in this case, the overall rate is the summation for both. So in that case, I will then have to take out because what is common in these two equations is K1 this and K2 of this. Oh, sorry, what am I talking about? What is common in these two equations is actually the first order with respect to the substrates. Yeah, so in that case, we'll have to take out the terms. Sorry, the stylus is not working very well. Okay, so my apologies if there's a bit of delay. Okay, so in that case, I will have to take out K1 from the first equation, and then I'll have to take out K2 sodium ethoxide from the second equation. Okay, and then I'll have the concentration of the substrates, which is the halogenal bromides. Okay, Br. Okay, yep. So that's how we show we can combine both to get this overall equation. Okay, then the next part we will have a table, 3.1, measured using different concentration of sodium ethoxide. You realize that the concentration of the substrate is in excess. Okay, so you are only varying the concentration of sodium ethoxide. Okay, so from here you are supposed to plot a graph to determine the value of K1 and K2. Okay, so you need to plot an appropriate graph. Okay, now you are given the rate over here. So assuming that this is the overall rate we are talking about. Okay, since you are given the overall rates, yeah. Okay, and then after that, you realize that the concentration of the bromides is a constant at 0.8. Okay, so this is actually a constant, which we don't really need to care about. Okay, then what we're going to do now is we can just plot the rates against the ethoxide, sodium ethoxide concentration. Okay, yeah, because if we are going to do it this way, what we are going to end up with would be an interesting graph. So we're going to have overall rates equals to K1, the substrate, I just write it as RBR, and then plus K2, RBR, okay, and sodium ethoxide, NaOET. Okay, I'm not expecting the concentration of the substrate to change substantially because it's in excess. So therefore, I expect these two values to be constant. Okay, so these two values to be constant. Yeah, and then now it makes perfect sense because if I'm going to plot, I'm going to get y equals to, this is C plus mx. Okay, so therefore, the gradient, which is the m, will give us K2 RBR, and then the y-intercept will give me K1 RBR. Okay, we're going to do a quick plot on this, okay, using the graph paper on this page. But I'm not going to include a lot of the details. Okay, so the x-axis would be the concentration of sodium ethoxide, NaOET, against, units moles per dm cube. So we'll start from 0 here. Okay, so pardon me if I don't write it in the correct significant figures because I'm just going to do a quick plot. So this is 0.040, 0.060, 0.080, 0.100, 0.120, and then 0.140. Okay, and then after that I'm going to just plot it over here. So I'm just going to write out the values. Okay, so I'm just going to do a quick one. So pardon me for the not so perfect job. Okay, so rates will be, okay, so rates, I will just write it as times 10 to the power minus 6, will that be okay? And then in terms of moles per dm cube per second. Okay, so over here will be 0 as well. Yeah, this will be 1.0, 2.0, and then 3.0, 4.0, 5.0, 6.0, 7.0, 8.0, 9.0, and then 10.0, then 11.0, 12.0. Okay, and then you notice that the numbers are actually quite nice. So you have 11 here and 0.1. So we have 0.1 over here and 11. So I think that's, sorry, okay, that's over here. And then we have another values here, 9 and 0.075. So we have 9 and then 0.075. So 0.075 will be somewhere in between over here. Okay, so this is 0.075. And then we have 0.05 and 7.00. Yeah. So 0.05 and 7.00. So we have this. Okay, so you realize that this is actually a very nice straight line. So if you were to draw it properly, this is what you should be getting. Okay, I think you can either use your actual use the actual graph paper given to you in the question paper. Okay, or you can draw. Yeah, so you should get a pretty nice straight line. Okay, and then you will get the y-intercept to be about 3.0. Okay, so with that, you can easily calculate the gradients. Okay, so then from here you can equate the gradients. Okay, so I've already done it beforehand. So you're going to get K2 bracket 0.80. You can equate it to the gradients. I mean that would be 1.1 times 10 to the power minus 5 minus 7.0 times 10 to the power minus 6 divided by 0.100 minus 0.050. Okay, so you can easily calculate K2 to be 1.00 times 10 to the power minus 4 per mole dm cube per second. And then you have gotten the y-intercept, which is 3.0 times 10 to the power minus 6, and then you can equate it to K1, 0.80. Why is it equating to K1? I think we have shown it earlier on, this portion. Okay, and then after that you can get K1 to be equals to 3.75 times 10 to the power minus 6 per second. Okay, and then after that, you are supposed to calculate the rate of the equation at 298 Kelvin when the concentration of the RBR is 0.6 and then etoxide is 0.150. So basically you are just equating to the equation. So therefore the rate is actually equals to 3.75 times 10 to the power minus 6, okay, plus 1.00 times 10 to the power minus 4 multiplied by 0.150 and then 0.60 for the concentration of the RBR. Okay, so the rate will be found to be 1.13 times 10 to the power minus 5 moles per dm cube per second. Okay, yeah, I think it's relatively straightforward. It's just that it's a bit troublesome. Okay, so my apologies, the line didn't come out so well because I'm using freehand. Okay, so I'm sure you can plot it and do a much better job than I do. Okay, so finally we have the last part. You have table 3.2 shows the percentages produced by each mechanistic pathway of alkenes A and B. Okay, so you're supposed to suggest explanation for these percentages. Okay, so there are many ways to do this particular question, and most of the students will get some marks. Okay, it will not be a 0. Yeah, most of the students will get some marks, but to get the full marks is not so straightforward. Okay, so why is that the case? Okay, because number one, right, I think you have to recognize that you are supposed to not only compare between E1 and E2, but you should also compare between the percentages of A and B. Okay, so I think for simplicity, let us just try to draw out A and B first. Okay, so I'm just going to draw this particular structure. Okay, and then we have a BR over here. Okay, and of course, I just label this as HA and this is HB. Okay, so if I'm going to eliminate HABR, then I'm going to get A. Okay, if I'm going to eliminate HBBR, I'm going to end up with B. Okay, I'm not showing E1 or E2 here, I'm just showing a generic removal of HBR in the course of the reaction. Okay, if you're astute enough, right, you will notice that the percentage of A is always higher. Okay, that can be easily explained because number one, this is by the Zaitsev rule. A is a tri-substituted alkene, whereas B is di-substituted. So a tri-substituted alkene is thermodynamically more stable as compared to a di-substituted alkene. So A being the major product, I think it's expected. Okay, so that's number one. Yeah, but of course, some of you might be wondering, is this a discussion on thermodynamic and kinetic product? Unfortunately, it's not a discussion on that. Because you see, regardless of whether this pathway goes through E1 or E2, right? The transition state leading to A will always be the more stabilized one. Okay, so let us just try to envision this. Okay, so if you're going to go through the E2, okay, let's say it's going to go through the E2, right? So your transition state will look something like that. You will have partial bond breaking of HA, partial bond forming of the pi bond, and partial bond forming of Br. And then, of course, your ethoxide will have a partial bond breaking with HA. So this is actually a transition state. You'll notice that this particular transition state, right, as opposed to a transition state that is like this. Okay, so let me just try to sketch it out. Okay, I'm trying to sketch it out. Now, this transition state versus this transition state, right? This will be the more stabilized one. Why? Because, right, the transition state resembles a tri-substituted alkene versus the one on the right hand side resembles a di-substituted alkene. Yeah, so going by this logic alone, right, E2, or rather A, the formation of A will be favored. Okay, you understand that? The formation of A will be favored by E2. Okay, going by the same logic, the transition states leading to A and B via E1, right, will also favor the formation of A. Why is that the case? Okay, if you look at the transition state, right? Okay, so this is a carbocation. Okay, this will be HB. This will be HA. Okay, so this is the carbocation. Yeah. So the transition states leading to A versus that leading to B, right? Again, one will resemble a tri-substituted alkene, the other will resemble a di-substituted alkene. Yeah. So the activation barrier will actually be lower as well. Yeah. So whatever the case is, formation of A will be favored. So there isn't much debate over this and much question to be asked. So if you are able to come up with this particular idea and explanation, I think you should be able to get 2 out of 3 marks quite easily. But the main thing is your seniors or the previous students taking this paper, right, they are not able to explain why the formation of A, right, is slightly more favored for E1 as compared to E2. You notice that there are more E1 products for A as compared to E2. So that's what you might notice. Okay. In that case, you need to make a brief remark on that. Although what you can argue here is just on paper, there's no way you can prove it or otherwise. Okay. So what you can say is that in terms of steric demand, okay, in terms of steric demand, it is easier to actually remove HA from the carbocation as compared to removing HA from the tertiary alkyl bromide. Do you all get that? Because in terms of steric, right, when you have a sp3 hybridized carbon surrounding it, it is actually slightly sterically more demanding to remove HA as compared to removing HA when you have a carbocation where it is quite spaced out. So let's say the carbocation looks like this. I'll draw the Me here, the Me. Okay, so this is the carbocation, and then I'm just going to maybe draw this group out like this, and then H here, and then H here. Do you all notice? In terms of sterics, it's actually easier to remove these two protons. And once it's removed, right, this sigma bond will then join this pi system, right, to form the empty p orbital to form the pi bond. Yeah. So in terms of steric, it is actually more favorable to remove HA from the carbocation as opposed to removing HA from the tertiary bromide. Yeah, so if you are able to explain that, then I think you should be able to get the full credit, because in that case, you have successfully accounts for why there is a slight difference in the in the greater percentage of A for E1 as compared to E2. Okay, so with that, that will be the end of question 3. So the next question we're going to look at is question 4. Okay, next we'll be looking at question 4. Yeah, so you have a diazomethane irradiated with UV lights, molecules split into CH2 and N2. You were told that the most stable electronic state of CH2 is the triplet state, where it exists as a diradical. So this is some new information you need to be aware of. Triplet state, diradical with 2 unpaired electrons. Another electronic state with an energy of 38 kilojoules per mole above the ground state is the singlet state, contains a pair of electrons. Okay, so the singlet state contains a pair of electrons. Yep. And then, so you were told that there are 3 possible structures of the central atom in the CH2 molecules. 1 with sp hybridization, 2 with sp2. So I think you need to follow this information. 1 with sp and then 2 with sp2. Okay, so you are told to draw structures to show the shapes of these 3 possible structures for CH2, including the unhybridized orbitals. Okay, so how can we do that? Okay, so I think the most important information here we need to provide the examiner is our understanding of hybridization and how we can use the valence shell electron pair repulsion theory to help us. But of course, valence shell electron pair repulsion theory is not important here because they are not asking to predict the shape, but rather they want you to incorporate your understanding of hybridization and then the placement of electrons, and in that case, try to explain certain things. Okay, I think later on they might ask you to, for each of the structures, suggest the number of unpaired electrons it contains, and then the likely HCH bond angle. Okay, so I think this should be it. Okay, it contains. Okay, so okay, let's try to do it over here. Yeah. Okay. So first of all, we'll try to work with the sp hybridized one first. So if it's sp hybridized, that means that the carbon will contain 2 sp hybrid orbitals, which will then be used to form sigma bond with hydrogen. Okay, so in that case, my structure will be linear. Okay, it will be linear. And then the 2 unhybridized p orbital will contain the electrons. So it will be like this, contain 1 electrons here, and then the other one will be orthogonal. Okay, contains 1 electrons. Yeah, so this will be one of the structures. Okay, if it is sp2 hybridized, okay, sp2 hybridized, then there are 2 possibilities. Okay, I mean, it's given here 2 possibilities, but even if they don't give you that information, you will be able to predict 2 possibilities as well. Okay, so both have bands shaped, okay, but one of it will contain an empty p orbital over here, and then the sp2 hybrid orbital, right, will contain the lone pair of electrons. Okay, then the other combination is that you'll be like this. Okay, and then you have a p here and the sp2 hybridized orbital over here. So 1 electrons here and another one with electrons here. Yeah, so these are the 2 radicals which we need to talk about, and I think the clue given above So let's just try to read the clue above again. The most stable electronic state is the triplet. So this is actually the most stable with the 2 unpaired electrons. And then above the ground, and then another electronic state with an energy 38 kilojoules per mole above the ground state is the singlet state with an unpaired electron. So this is the one which is 38 kilojoules per mole more unstable. Okay, so with that, I think we need to write down, give some information. So these are the structures which we have drawn. So it's best to actually tabulate the answer. Okay, I think that will be the easiest. Then in terms of hybridization, this will be SP, SP2, and this is SP2. Okay, then you have the number of unpaired electrons, number of unpaired electrons. So you have 2, 0, 2. Okay, and you are asked to suggest the bond angle. So suggest the HCH bond angle. Yeah. So in this case, it will be 180 degrees. Why is that the case? Because the repulsion sort of balance out. In our case here, the lone pair bond pair repulsion will be more significant. Yeah. So this will take on an angle slightly smaller than 120, so it will be 115 degrees. In our case here, the lone electrons bond pair repulsion is less significant than the bond pair repulsion. So we give it a greater bond angle than 120, so maybe 125, because we gave this as 115. Okay, yeah. Then what about the absorption? The types of absorption expected. Okay, so first maybe we want to indicate the number of absorption. Okay, because this contains 3 atoms. Okay, so it's linear. So for a linear structure, you have 2 absorption expected. One of it will be the asymmetric stretch, and then the bending modes. Okay, then for the other 2, you have 3 absorption. Yeah, because in addition to the asymmetric stretched, you also have the symmetrical stretched, and then the bending. Okay, so for the other one, it will be the same. Okay, so with this idea and this table, right, I think you can easily score your 8 marks, because if you look at the details that's required by the examiner, actually it's not a lot. You noticed. Okay, so I'm sure you can easily score the marks if you continue to apply the fundamentals of chemical bonding in your H3. Remember that in H3, they are testing you a lot on your fundamentals, just like H2. Yeah, and do not forget to revise your H2 when you're working for your H3 exams. Okay, moving on to the next part, we have a part B. Okay, you're supposed to use equation 4.1 to calculate the triplet singlet ratio. Okay, in a sample of CH2 at a temperature of 600 Kelvin, given delta G to be minus 38 kilojoules per mole. Okay, now you have to be really careful. Kilojoules per mole, you need to convert to joules per mole. Okay, so in that case, your K will be equals to 10 to the power minus. Okay, so remember this, 38,000. So this is minus 38 times 10 to the power 3 divide by 2.3 times 8.31 times the thermodynamic temperature. Anyway, they give it to you, is 600 Kelvin. Okay, then if you just punch your calculator, you will get 2060. Okay, so it's just a direct calculator punching exercise. But if you have gotten the wrong answer, that means that you forgot to convert kilojoules to joules. Yeah, so that would be quite fatal. Okay, the next part, part C, you have CH2 reacts with water to form methanol. So it's an energetics question. Okay, so you have equation 4.2 here. So they ask you to use the data given in table 4.1 and relevant data from the data booklets. Calculate the average CH bond energy in CH2, and then they ask you to show your working. Okay, so yep, if it's an energetics question, I don't think it's too difficult for you guys, H3 students, but anyway, we'll just slowly solve it. So we have CH2 gaseous plus H2O liquids, and then in the process we get methanol, okay, in the liquid state, and the enthalpy change of this reaction is given to be minus 346 kilojoules per mole. Okay, we'll see what we can do. Okay, so we are given the enthalpy change of formation of liquid methanol. Okay, so since we are given the enthalpy change of formation of this, so we'll try to work it out. So enthalpy change of formation of this involve carbon, which is a solid, okay, plus 2H2 gas, okay, plus half O2 gas. Okay, so the value is given to be negative 239 kilojoules per mole. So remember that in order for us to work through the problems, we need to create our cycle very slowly. Okay, so if you rush in completing your cycle, sometimes it will backfire. Okay, then can we try to compute the enthalpy change of formation of liquid water here? Okay, so yes, so let me just highlight this portion. So liquid water is actually like that, H2 gaseous and half O2 gas. Okay, so we can easily link this up. Okay, so we have enthalpy change of formation of liquid water, so that's given to be negative 286. Okay, so from here, we're not going to use all the H2, of course, so we are going to end up with H2O liquid, of course, and in our process, we are still left with H2 gas, okay, and of course a carbon, but this is in the solid states. Okay, so right now, are we in the position to continue to solve? I guess so, because the final thing we need to end up with is, maybe we can start with CH2 first. We want to break the CH covalent bond. Okay, so let the CH covalent bond energy be 2x, or you can just have BE of CH times 2. Okay, so in this case, I'm going to get carbon gaseous plus 2H gaseous plus H2O liquids. Okay, then so my final portion I need to link up, let me just write in green, will be for this portion over here. Okay, I'm just going to circle it, but obviously in the exam I'm not going to circle it like this. I'm just going to draw an arrow like this. Okay, so it involved atomization of carbon, which is 717, and of course the breaking of the HH covalent bonds. So we need to go back and look at the bond energy of HH, that is 436, so I'm going to input 436 here. Okay, and we are done, right? So we are going from, we're going in this direction, so basically we need to end up in clockwise, so like this, okay, right? So in this case, I'm going to get 2 bond energy of CH equals to minus 346, and then plus 239, minus 286, plus 717, plus 436. Okay, then you should punch your calculator, okay, and bond energy of CH, whatever values you get divided by 2, you should be able to get 380 kilojoules per mole. Okay, and this will be your average bond energy of CH in CH2. Okay, with that you can easily get your 3 marks. Alright, next we'll move on to question 5. Okay, we'll look at question 5 now. Okay, so for question 5, it's written that the hydrogen atoms bonded to the carbon atoms adjacent to carbonyl groups are slightly acidic. So those of you who are familiar with ketones, aldehydes, you will probably know the reason why the alpha protons are relatively acidic. It's due to the fact that the conjugate base is resonance stabilized. Okay, so without going into too much detail, this particular portion, right, if you actually sketch it out, it will look something like this with oxygen, and then this is the carbon with the H projecting inwards, with the H projecting towards you. Then it will have a lone pair of electrons on the p orbital, and then for the carbonyl group, there will be a CO pi bond here. Yeah, so this lone pair of electrons can be delocalized into the carbonyl oxygens because they can form a continuous overlap. Yeah, if you are interested, you can read a little bit more from Introductory Organic Chemistry textbook, where they discuss about alpha carbon substitution for carbonyl based compounds. Okay, of course, if you are not very interested, that's fine, because the question will have given you enough details for you to work through the problems. Okay, so for question 1, it's a relatively simple equilibrium calculations. You are asked to calculate the concentration of C when 0.01 moles of propanol is dissolved in 100 cubic centimeters of 2 molar sodium hydroxide, and then left for equilibrium to be established, and then supposed to state any approximation assumptions you made in your calculation. Okay, so I think the first thing we might want to do is to convert the amount of propanol into concentration term. Okay, so because we have 0.01 moles of propanol in 100 cubic centimeters. Yep, so in terms of concentration of propanol, you can easily calculate it to be 0.01 divided by 0.100. So you are going to get 0.100 moles per dm cube. Okay, so using simple acid-base equilibrium, you can easily, because you're given Kc, so you can easily write out a Kc expression. So your Kc expression will be Kc is equals to the equilibrium concentration of C. Okay, so that will be the equilibrium concentration of C. So that's equilibrium divided by the equilibrium concentration of OH minus. Yep, so that would be 2.0 minus the equilibrium concentration of C, because this will be the amount which ionize, okay, to give C. Okay, and then divide by this, multiplied by 0.100 minus of the equilibrium concentration of C. Okay, and you know the value of Kc, so you can easily substitute this in here. And then what would be your assumption? So of course your assumption is that the equilibrium concentration of C, right, this assumption over here, the assumption will be the equilibrium concentration of C is much smaller than 0.100 moles per dm cube. Okay, yep, so because if you are able to make that particular assumption, then you can actually easily calculate the equilibrium concentration of C, because in that case, you will simply just ignore these two terms. Okay, so if you work on it based on this assumption, you can easily obtain the equilibrium concentration of C Okay, so you can calculate it to be 1.0 times 10 to the power of minus 6 moles per dm cube. Okay, I wouldn't show you the working here because I think it will be, it won't be very meaningful because it's just simple calculations. Okay, so the next part we are going to look at will be the following parts where it was mentioned that the carbon anion C is an intermediate in many reactions, and then one of the reactions here will be the iodination. Okay, and then they said that further reaction with more base and iodine gives this product rather than this. Okay, now this is an interesting phenomenon here. Yeah, because I think before we delve into how do we solve this particular problem, right? You might want to be aware that having a minus charge here actually means, from what I've illustrated earlier on here, means that there is actually a lone pairs of electrons on the carbon atom. Okay, and in particular, it should be sp2 hybridized. Okay, and then how do we actually end up with this iodinated product? Well, it's basically some form of addition reaction. Okay, where this lone pair of electrons just attack the iodine, and then this iodine leave. Okay, you can also view it as some form. The overall is actually alpha substitution because the alpha hydrogen is being substituted with iodine. Okay, so it should be more of a substitution reaction rather than addition reaction. Okay, so we call this the alpha carbon. So this is known as the alpha carbon substitution. Yeah. So in this case, you produce the monobrominated ketone, and it was mentioned that if I actually subject this particular compound to more bases, right, I would actually end up with the product which looks like this. Okay, that means that the alpha hydrogen on the carbon directly bonded to the iodine, right, will further be deprotonated. Okay, so you get this rather than the other products. Yeah. So from here, right, I think if you recall what you learned in basic organic chemistry under the chapter, or rather not organic chemistry, but acid-base equilibrium, you probably know that what we need to do is to compare the stability of the conjugate bases. So we'll compare the stability of this conjugate base, okay, over or with this particular conjugate base, okay, with the lone pairs of electrons on the other carbon. Yeah. So you notice that for both conjugate bases, the lone pairs of electrons will be delocalized into the carbonyl oxygen. However, the one that is more stable is actually the one where the carbon bearing the negative charge is directly bonded to the iodine. Yeah. The reason being iodine is actually sigma withdrawing. Yeah, it's actually more electronegative than carbon. So the inductive withdrawing effects from iodine, or what we call the sigma withdrawing effect, right, will further help to disperse the negative charge of the conjugate base. Okay, so in that case, I expect this particular conjugate base to be more stable, and therefore you expect this to be formed, or rather this to be formed rather than this. Okay, so with that you can easily answer part 2. Okay, then for part 3, you are supposed to use the information to suggest the steps in the mechanism for the production of iodoform. Yeah, so this is quite interesting. You notice that this is one of the novel mechanisms being asked in H3. And some of you might have already learned this in school, or you might already have read about it in basic organic chemistry textbook. Yeah, but that is not the point, you see, because the point is being a fair exam, right? What if you have not gone through any of these textbooks or have not gone through this in school? Would you still be able to work on the problems? Yeah, so I mean, being a fair exam, there shouldn't be an advantage of someone who is more familiar and then memorize the mechanism somewhat and then has an easier time now. Yeah, so being a fair exam, actually, you do not need to have additional knowledge. You just need to use the above information to help you go through the whole process, and then you should be able to propose the mechanism quite easily. Okay, how can we go about doing that? Well, the first thing we need to be aware of is that this di-substituted iodo, right, or alpha di-substituted iodo, the first thing is that it has another alpha proton here, which I'm going to highlight in yellow. So this is the alpha protons. And from the above, right, you notice that there is a tendency for the alpha proton of the iodinated carbon to be removed for reasons being explained in part 2. So with that, then I'm going to expect this particular H to be removed, this particular highlighted H to be removed rather than the other one. And this is in line with our products, because you notice that for our products, let me just highlight in orange. For our products, right, this portion is constant. Okay, the CH3CO portion is constant. So that means that this particular portion is not being touched in the course of the reaction. Okay, or I mean, it could be touched, okay, but at least in the process of proposing the mechanism, then we have to focus on the task at hand. Okay, so with that, then perhaps we want to focus on the hydroxide base, removing this particular alpha protons. Okay, so this removal will be like this, and then we'll just follow whatever we have in front, because they prefer to put a negative charge on the carbon rather than push the electron density all the way to the carbonyl oxygen. Then we'll just do that. Okay, so we'll have this, and then what we're going to end up with will be the iodo here, and then with a lone pairs of electrons, okay, with a negative charge. Okay, so this will be the conjugate base which we are going to have, and then we are just going to continue with this alpha substitution reaction, where the lone pair will attack the iodine and then become tri-substituted. Okay, so with an I here, an I here, and another I here. Okay, so you notice that this portion, which I'm going to highlight in orange perhaps, this portion, right, is actually Ci3. Okay, so I'm just going to write in inverted column, Ci3. And Ci3, isn't it part of CHI3 here? Yeah, so eventually you'll know that the orange portion will give you iodoform. Okay, so if the orange portion gives you iodoform, right, then the next reaction where OH minus attacks, right, cannot be a normal kind of substitution or cannot be a normal kind of acid-base reaction. Okay, so in this case, it will have to be some form of a nucleophilic type addition at the carbonyl carbon, because remember, the carbonyl carbon, based on what I learned in H2, is still partially positively charged at the carbonyl carbon, right? So I'm going to attack. So we're just going to see what we'll end up with. And then from here, we're going to have O minus, and then I'll just write it as a Ci3, and then I have an OH. Aha! So in this case, can you see the form of some sort of a carboxylic acid is coming out already? So with that, then the lone pair of electrons will then push in, and then I will kick out this as a leaving group. And Ci3 minus as a leaving group is not too shady, because my negative charge in this case will be spread out by the three huge iodo groups. Yeah, so this huge electron cloud allows the negative charge to be kind of spread out, and at the same time, the inductive withdrawing effect of the iodo group will kind of make it, not as negative as it should be. I mean, it's not very stable, but at least it is still a relatively decent leaving group. Okay, so in this case, I'm going to end up with something like this, with a carboxylic acid, and then, of course, I'll end up with a Ci3 with a negative charge at the carbon. Yeah, and then obviously from here you can see that it will then undergo acid-base neutralization reaction. Okay, and then I will end up with carboxylate and CHI3. Okay, so I hope this mechanism isn't too daunting, because even if you are not sure what to do, having gone through the earlier parts allows you to, allows your thought process to flow in this manner, and coupled with whatever you have learned in the past about nucleophilic addition or addition elimination kind of mechanism, you should be able to propose a mechanism like this when the time comes. Okay, yeah. And some of you earlier on, when I was explaining, right, remember I said that this is known as an alpha substitution reaction when I formed this, and then if you kind of recall, I accidentally said that it's an addition kind of reaction, and then you might be wondering whether that's wrong. Of course, later on I corrected myself and I said that it will be more appropriately called an alpha substitution reaction. Yeah. Okay, I'm going to explain a little bit to you now. Actually, there's nothing wrong with calling it an addition reaction. For reasons you might be familiar with, depending on whether it was mentioned in the classes you experienced. Okay, now for a carbonyl compound, right, with an alpha proton here, if I have a base, it will remove this proton, yes. Okay, and then you can either push the arrows to here, and then you will get a negative charge over here. And then you said that this is resonance stabilized. How is it resonance stabilized? Well, this lone pair of electrons can be localized into the carbonyl oxygen, as what I show you in the orbital diagrams here. Okay, and then with that, I'm going to draw out this species like this. Can you see that this is like alkene? This portion is like alkene. Yeah, so we call this an enolate. Yeah, so actually there is nothing wrong in calling this reaction a electrophilic kind of addition reaction. Yeah, so that is also the problem about naming mechanism, because sometimes the same reaction, if it's being taken on at a slightly more advanced level, it can be named differently. And that is usually the problem chemists face. That's why IUPAC wanted to have a more uniform way of naming, but they have not pushed through. They are not able to push it through yet. Okay, and then you might be asking, so in that case, is it better for us, when we draw the mechanism, right? Is it better for us to push all the way to the enolate form? My answer to you is yes. Actually, it is more appropriate to draw it like this. Okay, to showcase the fact that actually the carbonyl oxygen prefers to take on the negative charge rather than the alpha carbon. Okay, but we did not draw this at the start, because the question stem showcased to us the negative charge at the alpha carbon rather than the carbonyl oxygen. Yeah, so this is to be more consistent with the question. Okay, so with that, we'll move on to the next part, B. Okay, so for part B, you are told that the hydrogen atoms bonded to a carbon flanked by two carbonyl groups are much more acidic. Again, the question did not ask you to explain, but you should be able to tell that this particular conjugate base, right, if it's formed, okay, so I'm just going to draw it here for convenience. It can actually be localized into both carbonyl oxygen. Okay, so I can actually draw a resonance structure like this, where I have an O minus here, okay, and the O ester, and then the negative charge can then be delocalized into the other carbonyl oxygen. Okay, so that is why the alpha carbon that is flanked by two carbonyl group is significantly more acidic than the other one that is only flanked by one carbonyl group. Okay, so I'm just going to erase this because I don't want this particular portion to affect the question later on. Okay, so along the way, we will of course discuss some things a little bit beyond the curriculum. Okay, and then you notice that this Kc value is huge, okay, much larger than what you expected earlier on, because earlier on the Kc value is in the region of 10 to the power minus 6. Okay, so the resulting N are your carbon analogues and useful nucleophiles and can react with halogenal alkenes. So this is obviously some form of a SN2 kind of reaction. Okay, so I'm sure you can tell that this acts as a nucleophile, and then this particular ethyl group is now being put here. Okay, then you are given the NMR, 1H NMR of compound F is shown in figure 5.1. Okay, and then the question is, you are supposed to assign the peaks A to F, okay, in the 1H NMR spectrum to appropriate protons in F and label them on the structure of F. Okay, so there are a few things we need to do here, because I think first of all it might be wonderful to draw F out. Okay. Okay, so the structure of F is over there. So I'm just going to sketch it over here. So I'm just going to draw the carbonyl group. Okay, and O, and then O ethyl, and then after that, so this is F. Okay. Now, which is the most obvious peak that I need to be aware of? So again, the way to do NMR is really there are like no trim and proper way of doing. Whatever ways you can do it in a systematic, or you can attempt it in a systematic manner, and you can get the answer, that means you are doing it the right way. Okay, and it is okay to have multiple approaches. So sometimes it's easier to use one approach, sometimes it's easier to use another approach. Okay, so for a relatively simple molecule like this, what I thought I would normally do is I will just examine the structure first, okay, and then just predict the multiplicity. I think predicting the multiplicity might be easier. Okay, so first of all, this particular protons here, right, there is no neighboring carbon containing H's, so I would expect this to be a singlet. Okay, and it should be relatively distributed. Okay, because the carbon is directly bonded to the carbonyl group, okay, which depletes the hydrogen, the alpha protons, the alpha hydrogens of its electron density by quite a bit. So I expect the chemical shift maybe about 2 plus, maybe 2.0 ppm, 2-ish. Okay, then the next thing I'm going to look at will be this particular portion. Okay, so this is the standard ethyl group bonded to an electronegative element. In this case is O. So an ethyl group, the splitting pattern is quite consistent. So the first portion is a quartet, the other one will be a triplet. Okay, and you expect the quartet to be very distributed. Why do you expect it to be very distributed? Because it is directly bonded to the oxygen here. Okay, which is a highly electronegative element. So you expect the chemical shift to be close to 4 ppm. Okay, for the triplets, you expect it to be maybe 1 plus something. Okay, yeah. And then you also notice over here that there is another CH3 here. Okay, yeah. So this is the part you have to be a bit careful about, because you might be thinking that these two ethyl group will share the same splitting pattern. Okay, truth to be told, they will not share the same splitting patterns. The reason is there is an additional proton here. Okay, there's an additional proton here, which will cause this CH2 to be a multiplet. Okay, so yeah, so it will not take on maybe 3 plus 1 or quintet or this. Yeah, because the two hydrogens here, the H here, they are in different chemical environments. So I don't expect the CH2, the H in the CH2 to be split in the same manner. Okay, and then if I want to compare the triplet here, and of course I expect this to be a triplet as well, and the triplet here, right? Which one will have a greater or more distributed chemical shift? So I expect this to be more distributed. Why? Because in terms of the relative distance to an electronegative group or electron withdrawing group, in that sense, it is closer. It's like just one position away. Whereas this particular H, right, is 1, 2, 3 positions away, and the 3 position away is not away from oxygen, but rather away from a carbonyl group. Yeah. So in this case, I expect this to be slightly more distributed than this. Okay, so with that, I think we can easily settle everything, because over here we have the necessary triplet in a 1:1 ratio. Okay, so these are the two triplets we're talking about. This triplet and this triplet. Yeah, so I would expect HF to be this. So this would So this would be HF, okay, and then the other one would be HE. So let me just erase some of the markings so that it's not so confusing. Okay, so so this will be HE, okay, and then the singlet here, the very obvious singlet here, this will be HC, okay, and then remember this quartet which I was talking about earlier on? Yeah, the one next to the ethyl group. Okay, so this would be HA over here. So this would be HA. And then the one that is flanked by the 2 carbonyl group, this 2 carbonyl group is flanking this single proton, right? So this is the single proton we're talking about. Okay, flanked by the 2 carbonyl group. So it will be distributed because okay, so this is the interesting thing that you might want to take note of. Yeah, so for example, right, you notice that HC, right, over here, I think the chemical shift is about 2.1. Okay, then some of you might be thinking, in that case, if this is flanked by 2 carbonyl group, right, then I will expect HB to be around 4.2. Yeah, but the actual HB is not 4.2. Is about 3.4. Yeah, so why is that the case? Okay, so I cannot give you a full view of this, but what I can tell you from research experience is that usually, right, if it's flanked by 2 or 3 of a common group, the hydrogen, in terms of chemical shift, right, will not be the same as the one with a single group multiplied by 2 or 3 times. It will not be like this. Usually, you need to give it a certain percentage of discount. So if you look at HB, right, you realize that it's about 20% discount, because 10% is about 0.42, so 20% is 0.84. So if you take 4.2 minus 0.84, you get about 3.4-ish or 3.36. Okay, so a general rule of thumb is that if it's flanked by 2 or more groups, usually it will be good to give it about a 20% discount. But this is purely empirical, okay, so there's no theoretical basis on that. Yeah, but if you want to make a good prediction of 1H NMR, this is a good strategy to employ. Okay, and then I think I named everything. Oh, there's one more. HD. Yeah, how can I forget the multiplet HD? Yeah, so HD is over here. So this is HD. Okay, which is a multiplet. Yeah, and you can see that this is not exactly a quintet, as we mentioned earlier on, because HB and HF are not in the same chemical environment. Yeah, so in terms of how they split the protons in HD, it will be split differently. Yeah, okay. If you go on to university level, you learn something called coupling constant. I think that will help you to understand this a lot more. Okay, and then part 2, we have a part 2 which asks you to explain the splitting pattern of peaks C and D. C and D. Okay, so I think I've when I'm trying to derive the structure for it earlier on, I try to explain to you. HC is like there is no splitting pattern because it is not bonded to carbon containing any H's. Okay, so there's no coupling expected. And then HD is a multiplet instead of a quintet. I think I also explained to you earlier on because HB and HF are in very different chemical environments, so you expect them to split HD up differently. Okay, and then what about the difference in the chemical shift of A and D? Okay, so for A, as I mentioned earlier on as well, when we try to elucidate or rather to assign the protons, the carbon where HA is bonded to is directly bonded to the highly electronegative oxygen, whereas for HD it is at some position away from the two highly electron withdrawing groups. So in that case, I expect HA to be significantly more distributed as compared to HD because the effect it felt from the two highly electron withdrawing group is not as great. Okay, so so some reasonings we have already discussed earlier on, so I hope it shouldn't be too difficult. Okay, so finally we have we are at part C, we are at 5C. Okay, so you were told that when heated under reflux with sodium hydroxide, F undergoes hydrolysis and decarboxylation with a loss of CO2 and a methyl ketone being formed. Okay, and then ask you to suggest a mechanism for step 2. Of course, you know that from here you expect CO2 to be formed because you were told that there's a loss of CO2. Okay, and obviously the CO2 must come from the carboxylates. Okay, so I think we can easily just push one arrow. Remember to draw in the lone pairs of electrons, and then you form the pi bond, and then in this sense, it breaks towards the carbon, the alpha carbon, and that is why there's a negative charge. The lone pair is not drawn for you, which is actually okay. Okay, so one mark, so one step, 2 arrows, 1 lone pair, I think that's fine. Okay, then after that, for part 2, you are asked to use the reaction in ABC to devise a synthesis of compound G starting from D. Okay, so you notice that for compound G, there are 2 additional groups being introduced. Okay, so one of them is a phenyl methyl group. Okay, this is a phenyl methyl group, and then another one is a methyl group over here, so maybe I color code with red. Okay, then what we have gone through thus far is all about alpha carbon substitution. So it's about deprotonating it using an appropriate base. In this case, it could be sodium hydroxide or it could be ethoxide. Okay, and then where do we get the idea of the ethoxide from? We get it from here actually. Yeah, I think earlier on there's one thing I forgot to mention. Ethoxide, if you have an ester here, over here, right, and in this case, ethyl ester, right, ethoxide is always a good base. Why? We tend to use the alkoxide related to the makeup of the ester. So if it's an ethyl ester, we'll use ethoxide. If it's a propyl ester or N-propyl ester, we'll use N-propoxide. If it's a methyl ester, we'll use methoxide. Yeah. The reason being, in case addition elimination takes place, right, we will not end up with a different ester. Yeah, we will not end up with what we call trans-esterification side products. Yeah. So just take note of this. Okay. So again, these are some of the things which you might want to read out, but if you don't read out, it's fine because they did not ask you for the details. Okay, so in this case, if I'm you, I would rather use an ethoxide. Okay, and then I will form the phenyl group. I will form the phenyl ring first. Okay, so what I will do is, I think in the most simplistic way, what I will do is I will introduce sodium ethoxide, okay, and then in ethanol, okay, ETOH in ethanol as the first step, and then after that I will introduce phenyl methyl bromides, okay, something like this. Okay, so with that I will be able to get this huge chunk in like this. Okay, yep. And then after that I will follow the above story. Yeah, remember, we must always follow the story, right? Yeah, so when we follow the story, we will need to generate something like this, and then we will add a methyl bromide in order to get my final group in. Okay, so first I will need to perform an alkaline hydrolysis. So sodium hydroxide, heat under reflux. Okay, heat under reflux, and then after that I will introduce methyl bromide. You do not need to give the details of the experimental procedure, because you are supposed to, or you're just asked to perform a synthesis. Okay, if you are interested to find out, you can actually Google it, because a lot of universities in their year 2 or year 3 undergraduate studies, they do such synthesis. Okay, but I can actually briefly tell you at least how this first step looks like. Okay, yeah, so usually you will use a round bottom flask with 2 or 3 neck, and then first of all you will dissolve D into an appropriate solvent. Okay, and then after that in one of the neck you will introduce sodium ethoxide in ethanol, and then you use a magnetic stirring bar to keep stirring the mixture. Yeah. In this case, you are generating the enolates, meaning that the conjugate base where this part is being removed. Okay, and then after that, slowly using another. After enough of D is being deprotonated, you remove the dropping funnel, and then you introduce another dropping funnel where you start to introduce this slowly. So you add dropwise, and then you will stir rigorously, and then you might just want to reflux at a fixed temperature. In this case, ethanol is probably about 78 degrees Celsius. Yeah, so you expect some form of SN2 to take place. Yeah, and then eventually you end up with this, and then of course you can test for its for the identity by either running through a 1H NMR, or you can if this is already a known procedure, you can probably do recrystallization to find out about the melting points of the unknown. Yeah, so there are many ways to do characterization. Okay, so with that we have come to the end of question 5. Next we're going to move on to question 6. Okay, so for 6A1 is a very H2-ish kind of question. You are asked to arrange the amines HIJK in orders of increasing basicity. Explain your reasoning. Yep. So to make things easier, let us just identify the phenylamine first. So phenylamine would be I and K. So we have phenylamine over here. So this directly bonded to the phenyl ring. Okay, so you definitely expect I and K to be less basic than H and J. Okay, however, you expect I to be the stronger base than K. The reason is now because the lone pairs of electrons on N will delocalize into the phenyl ring. Okay, however, the lone pairs of electrons on I will delocalize to a smaller extent because of the electron donating O methyl group. So the electron donating O methyl group will cause the lone pairs of electrons on N to delocalize to a smaller extent, okay, than that of the lone pairs of electrons on N in K. Okay, so in that case, in order of increasing basicity, I expect K to be less basic than I. Okay, and then between H and J, that's obvious because for the lone pairs of electrons, J is a primary amine, H secondary. So obviously, J will be less basic than H, and that's about it. Okay, so very H2-ish kind of question sometimes will be asked in H3, so I think you can easily get the 4 marks into your pockets. And then suggest a reagent for one-step conversion of J to H. I think you can easily do that with limited amount of bromoethane. Okay, so I think that should be fine, or you can just write bromoethane. Okay, doesn't really matter. Okay, and then the next part we're going to discuss will be a relatively interesting part, and I think quite a lot of students are not able to get the answers. Okay, so for B1, right, you were told that compound H reacts with iodomethane to form salt L. So, okay, so H is here. So this is H, okay, to form salt L. And then at room temperature, salt L is configurationally stable and its two enantiomer can be separated. Configurationally stable is it might be a new term. You might not have come across it. So this simply means that the two enantiomers do not interconvert readily. Okay, and then later on you were told that the free base, okay, the free base is not configurationally stable. So the two enantiomers will rapidly interconvert. The most important clue being given in this question, which I think a lot of students miss out, is this part. The interconversion occurs because the nitrogen undergoes orbital hybridization, similar to carbon. Okay, so this is the part which I think quite a lot of students might miss it out. And then if you kind of like miss this out, then you will not be able to get the answers. Okay, and then later on they ask you suggest explanation for these observations. Okay, now first of all, right, I think it is actually easier to work with L first. So let us try to do this by making our life a bit easier. So I will just let this whole group here be BZ. It's called a benzyl group. Okay, now first of all, right, we need to know that L is actually optically active, or it's actually chiral at the nitrogen. Why is that the case? Okay, let us take a look. You have a BZ here, right? And then there's a lone pair of electrons over here. Okay, now, so these lone pairs of electrons, okay, you cannot simply just turn it inside out, okay, as and when you want it. Yeah, because when you try to flip this group up, and maybe this group up, right, there will be electronic repulsion with the lone pairs of electrons. So the only way where you can do this kind of so-called flipping, please incorporate the inverted comma sign. It's not really flipping. Yeah, is for the nitrogen, right, to rehybridize. Okay, so in that case, right, we are going to change the hybridization state. Okay, where it could exist as a transient transition state. So for the nitrogen here, you expect it to be sp3, and then once it so-called turn inside out, it will remain as sp3. However, right, the transition states, okay, so this particular transition state, you expect it to be sp2. Okay, so in that case, I expect something like this. Okay, this projecting inwards, BZ here, and then projecting towards you. Okay, and then this lone pairs of electrons will now be in the p orbital. So in order for you to convert between the two enantiomer, it has to go through what we call a sp2 hybridized nitrogen transition state. And then after that, this thing will then be like this. Okay, the lone pairs will be like that, and then the BZ, and then this group projecting like that. And then you may be wondering, these two are different, but this and this are different. No, they are the same thing. How can we tell that they are actually the same thing? Can you try to imagine turning it 180 degrees? like that. Yeah, so if you try to turn it upside down, then you will notice that the lone pair will now be back here. Then whatever group that is projecting towards you will now be projecting away from you. Then whatever group that is projecting away from you will now be projecting towards you. Okay? Yep. So in short, in order for me to interconvert between the two enantiomer, it will have to go through this trigonal planar transition state where the nitrogen is sp2 hybridized. And this is only possible if the lone pairs of electrons is there. If the lone pairs of electrons is not there and you are already forming a bond, in this case with an H, then the interconversion will not be possible. Yeah, because for you to interconvert like this is the same as converting between two tetrahydrocarbon where you need to overcome bond. I mean, you need to take in energy to break some bonds, but such interconversion shouldn't involve bond breaking. Okay, so you should take a bit of time and maybe you pause the video for a while to think about what we have gone through. Okay, so in short, maybe I can just repeat a little bit. For the free base of L, it is easy to interconvert because the barrier is likely to be low, where the nitrogen will rehybridize from sp3 to sp2. So you will get this trigonal planar transition state, and then after that, you can just flip over, the thing can be turned inside out, and then you get the other enantiomer. So this can be done quite easily. How do you know? The question told you so. So the barrier is likely to be low. For the salts, it is likely to be very stable because any form of interconversion will likely to involve some form of bond breaking, which you need to incorporate energy to the system. Meaning you need to perform some heating up, all this, which definitely at room temperature, the amount of heat in the surrounding is insufficient for such conversion to take place or for such bond breaking to take place. Okay, so therefore it remains configurationally stable. Yeah, okay, so you might want to just take a bit of time to think about it and see whether it makes sense to you. Okay, and then moving on to part 2, again, it's definitely not a difficult question. It's a recall question, in fact, using the RS configuration or the convention, assign the absolute configuration of enantiomer I, okay, or enantiomer 1 of salt L. Okay, I think you can quite easily do that because let's just run through it quite fast. Okay, so first of all, hydrogen of course has the lowest atomic number. Okay, so you will take on priority for the least, the one with the least priority, and then there are 3 carbons here, so both of them with atomic number 6. Okay, but when we have the carbon with the, or rather we are bonded to the group with the same atomic number, then we need to move on to the second layer in order to differentiate the two. Okay, so so let us try to write them out. So for this case, we have H, H, H. Okay, so that's for the first carbon, the methyl group. Then for the ethyl group, we have C, H, H. Okay, then for the benzyl group, we have also C, H, H. Okay, so in this case, we are able to differentiate the methyl group, so therefore the methyl group will take on the priority of 3. Okay, and then the next layer we need to go will be we need to move on to the next layer because this particular layer we can't differentiate. So the next layer we will have a carbon. Okay, and of course this particular carbon is bonded to 3 H's. But for benzyl, if you expand it, this carbon will be bonded to many other carbons, so in fact all carbons. So therefore benzene will take on first priority, and then this will take on second priority. Okay, so with that, if we assume that N is the center, now we put the groups away from us. Then we have priority 2 over here, priority 1 over here, priority 3 over here. So we go from 1 to 2 to 3. This is in an anti-clockwise manner or counter-clockwise manner. So therefore, the configuration but using the CIP convention is actually S. Okay, and that's it for part 2. And then part 3, you are asked, or you were told that enantiomer 1 and 2 of salts M are configurationally stable at room temperature, but interconversion occurs at 100 degrees Celsius. So again, when you raise it up to appropriate temperature, the activation barrier is overcome so that bond breaking and bond forming is possible. They ask you to suggest a mechanism for this observation, given that the first step involved the attack of CC by I. So again, I minus, sorry. This wouldn't be too surprising because I think first of all, right, you need to attack the CC double bond. Why is attacking the CC double bond important here? Or why do they need to tell you? They need to tell you this because you need to be aware that a side product, or rather, this will be one of the products being produced along the way, and then it will react back again in the course of the reaction. Okay, so we need to be aware that this nitrogen taking on the positive charge, right? This is what we normally call an electron sink. Okay, so an electron sink is when electron density is being pushed towards it. Okay, so since we were told that the CC double bond is being reacted, right? So these lone pair of electrons will attack this, okay, and then the pi bond will shift, and then the lone pairs of electrons on N will be generated, or the N will actually form back the free base. Okay, in that sense. Yeah. So in the course of reaction, what I'm going to get is I'm going to get the N here, and then this group projecting, and then benzyl, and then with a lone pairs of electrons over here, plus this particular group. Okay, the allylic iodo group, and then as what we have learned earlier on over here, so you expect the conversion to take place, so you will undergo this particular transition states so that I'm able to get the other enantiomer. So I'm going to show the conversion. So this is BZ like that. Okay, this transition state, and then I need to be able to show this. Okay, with the lone pairs of electrons now over here, and then BZ, and then like this. And then with this iodo group, I will then perform this SN2 prime kind of reaction. Okay, then I'll kick out this group. Okay, so with that, I will generate this. Then some of you might be thinking it looks quite different, but you should redraw it to tell. Okay, so I'm going to get this, and then like this. Okay, so remember these two are the same because whatever that is projecting out away from you, if you flip it over, it will now project towards you. Then whatever group that is projecting towards you, when you flip it over, it will now be projecting away from you. Okay, so this is the thought process that you might want to go through. And of course, how do you know that it must undergo this transition state? Well, I mean, if not, how will you end up with the enantiomer? And then the first step is already told to you, when involved in nucleophilic attack of CC double by I minus. Yeah, since the first step is being told to you, then you should be able to visualize that you should be able to visualize that. First, I need to generate the free base, and then from the free base, it must undergo the flip, the structural flip, meaning you need to turn the structure inside out. You will have to the sp3 hybridized nitrogen will have to rehybridized into sp2 hybridized transition state, and then you will then rehybridize back to sp3, and then that particular base will then undergo another form of SN2 or SN2 prime in order to get enantiomer 2. Some of you might also be wondering, why is it so perfect? Will there be a situation when this free base attack this back? Yes, you can. You can attack back and then you get back this. So it doesn't really matter. If you get what I'm trying to say. Yeah, it doesn't really matter. Yeah. So that is why they mentioned that this conversion occurs at 100 degrees Celsius because it's only at 100 degrees Celsius that perhaps this reaction can take place. And then after I form this, maybe in that split second, it will attack it back and then give you back this, is fine. Okay, if it doesn't, it can flip, and then after that, I can then perform SN2 prime and then to get this. So that's perfect as well. Okay, yeah, and then let us move on to the last part, okay, which is part C. Okay, so for C1, right, the first portion is not difficult at all. It's actually H2 chemistry, and you were asked, amide N cannot be prepared by the direct reaction of benzoylamide and ethanoic acid. Obviously, you know why, because benzoylamide is a base, ethanoic acid is a weak acid. So you put the two together, they will undergo acid-base neutralization. Yeah. So an alternative way for this particular transformation, right, instead of using ethanoic acids, I should use ethanol chloride. Yeah, so ethanol chloride will be able to give me N. Okay, then after that you are given the next part, infrared absorption frequency of the carbonyl units in N, propanone and O are shown in table 6.1. You are asked to suggest why the infrared absorption frequency by the carbonyl units in N is less than the frequency of the carbonyl unit in propanone and O. Okay, so first of all, right, we need to compare correctly. We need to compare N with propanone. Okay, so we need to compare these two first. I think we need to be very clear what we are doing. Okay, and then we need to compare between N and O. Okay, so I think once we get the correct idea, I think it should be we should be able to do it quite easily. Okay, so first of all, right, why is the infrared absorption frequency in amide significantly lower than 1700? Because 1700 is the usual wave number for carbonyl group. Well, that's because of the fact that the lone pairs of electrons on N is delocalized into the carbonyl group, and in this case particularly carbonyl oxygen. And this delocalization actually gives the CO bond a partial single bond character. So the weakening of this CO bond actually led to a lower absorption frequency than propanone. So I think we can understand that quite easily. Okay, what about an ester? Okay, what about an ester? Like O is an ester, right? Okay, so O is, in this case, it's a little bit different. You notice that O, for O, right, it is significantly higher than the mainstream carbonyl group. So usually CO stretch, if you look at ketones and aldehydes, is about 1715 or 1710 or 1700. Yeah. CO is actually around 5% higher. That's about 1745. That's the usual range we are looking at. Why is that the case? Well, that is the case because the oxygen over here, right? Okay, so this particular oxygen, is able to inductively withdraw electron density towards it. So this inductive withdrawing effect, right, will actually strengthen the CO bond. So, or strengthen it slightly. So this slight strengthening, right, actually results in a greater absorption in terms of the frequency. So because of strengthening, so therefore the CO actually stretches higher at a higher frequency than that of amides and ketone. Okay, but then you might be wondering, then in end, wouldn't the inductive withdrawing effect happen also? But you need to be aware that nitrogen is actually less electronegative than oxygen. Yeah, so therefore the pi withdrawing effect in CO actually dominates. Yeah, however, on the other hand, right, these two oxygen are quite similar, right? Or rather similar in terms of electronegativity. So I wouldn't expect the CO withdrawing effect to dominate over the inductive withdrawing effect. Yeah, so with that reasoning, I hope you are slightly clear why there's a difference in the infrared absorption frequency. And then for part 3, you're supposed to predict which compound N and O undergoes reduction faster when treated with lithium aluminium hydride in dry ether, right? Okay, so in this case, I expect O to be reduced faster as compared to N, and the reason is because when you look between N and O, right, between the amide and the ester, right, you expect the carbon in ester to be significantly more electron deficient due to the stronger electron withdrawing effect of oxygen. Okay, so therefore the carbon in O is more susceptible to nucleophilic attack by the hydride, or you can say more susceptible to the reduction or to reduction by lithium aluminum hydride. But you should probably be aware that the reduction by lithium aluminum hydride is actually performed by the H- equivalent of aluminum hydride. Okay, so with that, we are done with question 6. Okay, next we are going to talk about question 7. Okay, so for question 7, you are given this particular molecule. I think you are given the configuration S2 iodo-propane. Okay, so you were told that it reacted with sodium methoxide to give 2-methoxy-pentane, a process that could occur via either SN1 or SN2. Okay, so before we even start working on the problem, it might be good to sketch out the structure of 2-iodo-pentane. Okay, so basically we have a pentane molecule over here, 1, 2, 3, 4, 5. Okay, so maybe it's easier to do it the other way around. So 1, 2, 3, 4, 5. Okay, at the second position is the iodine. Okay, so assuming that now the iodine projects away from us, okay, then the H will project towards us. Okay, so now let us try to assign the priority. Okay, so iodo group will have priority 1, and then the difference between this C and this C is that this particular carbon, the next level is actually bonded to 3 H's, and then for this particular carbon is bonded to 1 carbon and 2 H. Okay, so in that case, this will have priority 2, priority 3, and then of course H will have priority 4. Okay, so now if we just look at the structure like that from 1, 2, and 3, it's clockwise, so by right it should be R. Okay, however, because the H is now pointing towards us, if the H is pointing away from us, it will be going from clockwise to anti-clockwise. So in this case, it will take on the S configuration. Okay, so this is the correct structure. Yeah, so this is one way where you could attempt to try to sketch out the structure and see whether you're on the right track. Yeah, so we are either right or wrong. So you just sketch something out, assign the priority, and then after that check it out. Yeah, so this is one of the method which I often use. Okay, so for 7A1, you are supposed to draw the energy profile diagram, provide the Rates law for each of these pathways. Okay, so I think I will attempt to answer the rate law first because it's the easiest. Okay, so therefore for SN1, the Rates law will be rates is equals to K1 because it's SN1. Okay, and then so you can spell everything out if you want to. Iodo pentane. Okay, or you can just put it as Ri lah if you want. Okay, then for SN2, the rates will be equals to K2, and then S same 2 iodo pentane, and then first order again. Okay, let me write it below, and then first order with respect to the sodium methoxide, so that will be NaOMe. Okay, so this is the way you can write out the rate law. So in that case, I have already answered this. Okay, so I'll just move on to draw the energy profile diagram. This should be relatively H2-ish, so it's not really H3 stuff. Okay, perhaps just a little bit of things you need to take note of. Okay, so again, energy profile diagram, we need to have energy here in terms of kilojoules per mole as the units, and then remember the x-axis is actually what we call the reaction coordinates. Okay, or the reaction pathway, but the more accurate term is the reaction coordinates. Okay, so let us just attempt to draw out the SN1 pathway, because the SN1 pathway is the slightly more complicated one. Not complicated, but it's longer. Okay, so we'll attempt to first label our starting material. Okay, so our starting material should be over here. So I will just sketch out the iodo. Okay, so this is the I, and then NeO minus. Okay, I would expect the carbocation, because being SN1, you generate the carbocation first, right, to be of a higher electronic energy, or of a higher energy as compared to the rest. Okay, so in this case, I will attempt to showcase the trigonal planar geometry of the carbocation. For reasons where I'm going to explain to you later on. Okay, so sorry, this is the H is actually here. If you look strictly at it, okay, so the H is here, and then we have a plus charge, and then we need to balance the mass, so we have I minus and then the NeO minus here. Okay, and I expect my products to be more stable. In fact, I should draw it much lower. Okay, to be more stable. For a simple reason, because the CO bond is stronger than the Ci bond. Okay, yeah, so I'm just going to sketch this out, and then O, M, E, and then like this. Okay, and I minus. Okay, so technically I should get a racemic mixture. So the proper representation for a racemic mixture should be something like that. Okay, with a wicked line. But this is not hot to you in H3. So in that case, we will avoid drawing it. So we'll just draw it as a normal structure where we just don't showcase the stereochem. If you want to show both stereochemistry, it's also perfectly fine. Okay. Then over here, I think the first thing we're going to do is we will draw out the transition states. Okay, some of you will be wondering, is the transition state necessary? Well, I mean, it's good to show because after all, it's 4 marks. So I think they do value some details required. Okay, so so we'll just draw dot I. Okay, so this is the transition states showing us where the Ci bond break to a relatively large extent. Okay, then in that case we'll try to connect these two parts up. Okay, sorry, it's a bit difficult to draw using the stylus. Okay, so pardon me for the not so straight line. Okay, then the next transition state I'm going to draw will be showcasing the top and bottom attack by OME. Okay, so in this case I'm going to draw this and then pointing in, and then the H, okay, and then the MEO partially attacking the carbocationic center, okay, and then of course with the I minus here. Okay, so it will be like this and then like this. Okay, and then of course there should be another transition state here showing the bottom attack. Okay, so I will showcase it like this, and then dot 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 OME, and then transition state. Some of you might be wondering, right? Shouldn't this particular portion like be pointing down a little bit? Okay, yes, you are absolutely right, but for H3 we don't learn all this in such great details. Yeah, so in that case we try not to draw the transition state which resembles reality as much. Of course, if you want, you can, especially in this case, but if you don't wish to, I think this is perfectly fine. Yeah, so if you wish to, then yep, you can actually tilt it a little bit. Then I think it will showcase reality a little bit more if you want. Yeah, so I think it will look a bit nicer like this. Okay, so again, it's personal preference. Okay, so there's no hard and fast rule when it comes to this. Okay, yeah, right, and then that's it. Yeah, that's it for SN1. Okay, for SN2, it will be very, very similar to again what you learned in H2. So we have energy here in terms of kilojoules per mole, and then we have reaction coordinates in the x-axis. Okay, and then of course same story, but the story in this case will be a little bit different because where possible, right, I want to sketch it in such a way that I can easily draw my SN2 transition states showcasing the rear attack. Yeah, okay, so I think the easiest way is really to sketch it out in such a way where the eye is pointing to the right or left. It's really dependent on your preference, how you want to draw it. Okay, so all these cases, it is very human dependent. Okay, like very student dependent. It's based on your style, so you need to develop your own style, develop your own voice when it comes to drawing structures and transition states. Okay, and of course you know that for rear attack, it's going to result in an inversion of stereochemistry. So I'm going to showcase it like this. Okay, so 1, 2, 3, 4. Okay, and then of course pointing down, and then this is pointing away. Yeah, so stereochemical inversion plus I minus. Okay, then my transition state. Okay, I don't have space here, so I'm just going to draw it over here. So again, the transition state is pretty much what you are used to. So you have dot 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 the carbon here, and then after that the iodo group is also living, and then we have 1, 2, 3. Okay, and then we have the H pointing away, and then the methyl group pointing towards us. Okay, and then overall minus charge. 2, 3, 4, 5. Yeah, okay. So this is the transition state we're looking at. Okay, yeah, it's a bit boring, I agree. Very H2-ish. Why is it H2-ish? Because I guess for H2, you'll be familiar with drawing this. Maybe for H2, not so familiar with drawing the SN1 transition states. Yeah, but it's perfectly fine. Okay, yeah. Okay, it's a bit messy, but I just hope you can see question A2. You are asked to describe the stereochemistry of 2-methoxypentene formed by each of these two pathways. Okay, so for the case of SN1, you would expect both the R and S isomers to be obtained in almost equal proportion. Yeah, I mean based on what you have learned, because for SN1 it goes through an intermediate which is trigonal planar in geometry about the carbon bearing the positive charge. So you would expect the methoxide to approach it from the top and bottom plane with near equal probability. But for SN2, it's a rear attack. Yeah, so you will get stereochemical inversion. Yeah, so for the case of this, I expect an inversion of stereochemistry. So my final product is exclusively R. Okay, so that will be your answer to part 2. Moving on to the next question. Okay, so you are given table 7.1, which show the data for the nucleophilic substitution of a 0.01 moles per cube solution of S-iodopentane. So now it's abbreviated to SRI. Okay, and then with a large excess of sodium methoxide. Okay, so in this case, this is a pseudo nth order reaction with respect to the iodopentane. And then 2 runs were conducted at constant temperature. One with 1 mole per cube of sodium methoxide and one with 2 moles per cube of sodium methoxide. So samples were taken every hour and the percentage of S2-iodopentane remain was measured. So you are asked to suggest an analytical technique you could use to measure the percentage of S-iodopentane remaining at each time in table 7.1. Okay, so you will realize that in the course of the reaction, if you just look at above, the iodide group is being produced. Okay, so this iodide anion is being produced. So in that case, we could leverage on this, okay, by using gravimetry. Okay, so that will mean that at hourly interval, I mean you can write it in a relatively simple way. At the hourly interval, you can just abstract a certain volume of aliquot out, and then you'll be good to quench, okay, either in a copious amount of water or something. Okay, so you just quench it in large volume of cold water, and then after that you add excess silver nitrates, okay, and then you would expect silver iodide to be precipitated out. Okay, then from there you can actually weigh. You can, I mean, the filter, you can dry, and you can weigh the silver iodide precipitated out, and then after that you can convert the mass of the silver iodide obtained, and then from then on it will serve as a proxy to the amount of S-iodopentane remaining in the solution, and then after that, from there you should be able to monitor. Okay, because once you know the amount of S-iodopentane remaining in the solution, that allows you to track how it varies over time. Okay, so that will be one method which you could use if you wish to. And then if you think about it, after you quench it, you have iodide in the solution. Another way, if you wish to do it, but it's a slightly more complicated way, but more accurate, yeah, is to add in an oxidizing agent which will oxidize iodide to iodine. H2O2 will be a good choice, okay, or you can use iodine if you want, but I think H2O2 is a better choice, and then after that you can perform iodometric titration. Yeah, it will be a more accurate method because titration, the precision is there. Gravimetry, we will always run into the risk of losing some samples. So these are the limitations which you need to be aware of. Okay, then moving on to part 4, right? Over here, you were told that assume that the optical rotation of S2-iodopentane and S2-methoxy pentane are equal in magnitude and opposite in sign. Okay, so you were told that at T equals 0, the reaction mixture has an optical rotation value of plus 100 degrees. Okay, so that means that Okay, so maybe to make it simpler, I'll just write it out above. So that means that for S2 iodopentane, I expect the optical rotation value to be plus 100 degrees. Okay, and then we were told that S2 methoxypentane are equal in magnitude but opposite in direction. Okay, so in this case, S2 methoxypentane would be minus 100 degrees. Okay, I hope you will agree with me on that. Okay, and then I'm supposed to determine the optical rotation of the mixture at 50% conversion, okay, of S2 iodopentane when the process occurs via SM1. Okay, so what is the meaning of 50% conversion? So 50% conversion means that I will still have 50% of S2 iodopentane. So that means that I need to multiply 100 plus 100 degrees by 50%. Okay, so that is plus 100 degrees. Okay, and then 50% of it is being converted to the product which contains both R and S2 methoxypentane. Okay, so each, because you assume that each will be in equal proportion, so you have 25% of each, so 25% of this, okay, and 25% of the other one, so which is minus 100 degrees. So if you quickly punch your calculators, you should be able to get plus 50 degrees, okay, as the answer to the first bullet point. Okay, if it's a pure SN2 pathway, okay, so same narrative, so we have 50% of it remaining, okay, 100 degrees, okay, and then we have 50% conversion to the R isomer. So if S is minus 100, R will be plus 100. Okay, so we'll end up with plus 100 degrees. Okay, so I hope this is relatively simple arithmetic for you to solve. Okay, then now comes the most important question, which is worth 5 marks. Okay, so it's worth 5 marks over here. It's a crucial 5 marks. So not asking to spam details, but there are quite a bit of things which you need to write in order to showcase your thought process well. So you are supposed to use the data in table 7.1 to determine whether the process occurs via SM or SM2. So explain your reasoning fully. Okay, now first of all, right, before we even go about explaining, I think earlier on you heard me mentioning one thing, is a pseudo nth order reaction, right? Because first of all, we are using 0.01 moles per dm cube of S2 iodopentane, and we are using 1 molar and 2 molar of sodium methoxide. Okay, so that means that if I'm going to write a Rates law out, right, it will be Rates equals to K iodopentane raised to the power of M, and then sodium methoxide, that will be Na or OMe raised to the power of N. Okay, however, because the concentration of sodium methoxide is way greater than the concentration of the iodopentane, therefore, right, my rate law can be simplified to rates is equals to K prime Ri M. So this becomes a pseudo nth order reaction with respect to iodopentane. Okay, now let us try and see if this makes sense, okay, by looking at the graphs. Okay, so if we look at the graph, right, you realize that when we start off with 100% of S of Ri, and then after 2 hours you are left with 50%, and then after another 2 hours you are left with 25%, and then after another 2 hours you are left with 12.5%. So this actually tells us that there is actually a constant half-life. Okay, when the concentration of sodium methoxide is 1 mole per dm cube. So this is a constant half-life. So so we can simply just look at the row I put with a star, and conclude the order of reaction with respect to S2-iodopentane. Yeah, so from here I can conclude that M is equals to 1. Okay? Yeah, I forgot to put here that your K prime, although it's quite obvious, but I thought I just want to put it in, is actually K and A. Okay, so there's no space, sorry. So this K prime, right, is K prime is equals to K N A O M E N. Okay, can? So it has a constant half-life of 2 hours. Okay, so therefore it's pseudo first order, or rather first order with respect to iodopentane. Okay, if you wish to use the second row, it's also perfectly fine. Okay, perfectly fine. But for the second row, you realize that now the T half, right, decreases to 1 hour. Okay, it decreases to 1 hour. Okay, but it's still a constant half-life. Okay, so let me repeat. It's still a constant half-life. So whether you use the first row, which I put with a star in green, or the second row, which I put with a star in orange, right? Regardless of whether you use that row, I mean, the first row or the second row, right? You will still be able to conclude that M is equals to 1 by virtue of the fact that the half-life is a constant. Okay. However, you will not be able to conclude the value of N, which is the order of reaction with respect to sodium methoxide, by simply looking at individual rows. You will not be able to conclude. Yeah, you will only be able to conclude if you look at both together. If you look at both rows together. Okay, why is that the case? Okay, so let me just explain over here. Okay, so from the pseudo nth order reaction, or rather pseudo first order, right? From here you can conclude that T half is equals to ln 2 over K prime. Okay, yeah. So what this means is that the change in the concentration of S2-iodopentane, right, has no effects on the half-life. Okay. However, right, we need to expand K prime. We will expand K prime to give us K and then sodium methoxide to the power N. Yes. So you notice that the half-life, right, in fact, is actually dependent on N, or rather the concentration of sodium methoxide. Okay. And you notice over here that when the concentration of sodium methoxide doubles, the half-life actually halves. So from here it tells us that N is actually equals to 1. Okay, and this is very important information. Yeah. So again, if you are not so sure what exactly is going on, please revise and review your H2 kinetics stuff, because this is really kinetics at its best, or at its most fundamental concept, where you are required to determine the order by simply looking at data. Okay, so M is 1, N is 1, so therefore it occurs via the SN2 pathway. Okay, and I have already explained to you the thought process, so I think drafting out the answers wouldn't be too difficult. Next, I'll move on to B part 1. Okay, so it reads, I have a compound P exists in 2 predominance conformations. So you have conformer 1 and conformer 2. You are asked to explain why conformer 1 is preferred, and then very importantly, your answer should include appropriate Newman projection. Okay, this is very important, because if you don't draw in the Newman projection, I'm just afraid that you probably wouldn't be able to get any significant marks. Okay, so in case you're not sure how to draw in the Newman projection, so we can do a little bit of revision over here. We'll just look at conformer 1 directly, okay, from this structure. Okay, so I'll just zoom in so that it's clearer. Okay, so first of all, right, how do we draw it? I will just include in the relevant H's first. Okay, so the H is here, so let me just draw in this H. Okay, and of course, perhaps the H pointing up, and then and the H over here. Okay, maybe I should color code those at the back so that it's easier. So those in front, I'll just put in green. Yeah, those at the back, I'll just put in maybe orange. Okay, so over here, and then over here, and over here. Okay, yeah. So now I'm going to look at carbon number 1. Okay, I'll place carbon number 1 in front, and then carbon number 6 will be at the back. Okay, so this is how it will look like. Okay, so first of all, I will have a Newman projection like this. Okay, and then I'll have the bulky group like that. Okay, and then pointing down will be in green. Okay, so this will be in green, and then those at the back will be in orange. Okay, so it will be like this and like this. Okay, and then I will just sketch out the rest of the structure out, so like that. Okay, and then this portion in green, and then this is in green. Okay, so in case you are not clear about the numbering, this is actually carbon 1, this is carbon 2, this is carbon 3. That's why it's in front of you. Okay, can you see? It's like, it's the first carbon you witnessed. Okay, and then those at the back will be 6 at the back, and then after that this is actually 5, and then then this will be connected to 4, and then 4 at the back, the H will be here, and the H will be here. Okay, so this will be carbon number 5. Okay, I can't label 6 and 4 because they are behind 1 and 3, so it's a bit difficult to label. If I'm going to label it, it will be very confusing. Okay, so yes, so this is the answer you're supposed to give for the first conformer, for conformer 1. Okay, then of course, if you are able to draw this, then obviously drawing conformer 2 wouldn't be a major issue. Okay, so to draw conformer 2, this is what I'm going to draw. Again, same thing, like this, and then draw this huge group out. Okay, and then like this. Okay, then of course like this, and then I'm just going to showcase the rest of the groups. So this would be H here, H here, and then H here, and then H here, and then I'm going to show the H here, and then H is here, and then H below. Okay, yeah. So for those of you who are a little bit confused, maybe I should just number it as well. 1, 2, 3, 4, 5, 6. So I'm going to number this as well. 1, 2, and then 3. 4 is behind 3, so we can't see it. So 5, and then we can't draw. I can't label 6 because 6 is behind 1. Okay, so these are the 2 appropriate Newman projections which you should include in your answers, and I guess they carry some marks. And then after that, you need to explain why. Okay, so the explanation wouldn't be too difficult, right? Because the main emphasis is actually on the 1,3 diaxial interaction. Okay, now in this chair conformation, right, we can easily indicate the 1,3 diaxial interaction by drawing the axial H's. Okay, so these are the axial H, and then normally in school or in tutorials, we will normally just say that this is the unfavorable 1,3 diaxial interaction. Okay, so for conformer 1, you are minimizing 1,3 diaxial interaction, but for conformer 2, the 1,3 diaxial interaction is kind of quite obvious. Not exactly maximized, but yeah, it's quite obviously seen over here. So so what do you notice here is that the 1,3 diaxial interaction is actually over here and this H. Okay, if you want to emphasize on this H, you can draw out this, and then you can also indicate that for carbon number 5, the axial cage, okay, also interact via the 1,3 diaxial interaction in an unfavorable manner. Yeah, of course, that is if you wish to indicate it. Okay, yeah, so that will be for part one. I hope it's not too daunting, because I mean, sometimes drawing chair conformation and then converting it to Newman projections is a little bit difficult for most of the students. But maybe I would like to urge you to ensure that your fundamentals in doing this is actually sound, because most of the time H3 actually tests the students on fundamentals. Okay, the next part we are going to deal with will be part 2. You are being told that when treated with a non-nucleophilic base, a non-nucleophilic base basically is a base that is a poor nucleophile, okay, because it has a bulky group. Okay, so I think it's mentioned very explicitly, abstracts a proton from the hydroxyl group. Okay, then you were told that compound Q forms R quickly. Okay, so the keyword is quickly. But the conversion of S to T is much slower. So you were asked to suggest a mechanism to explain these observations. Okay, so what is most important is to draw out the correct conformation. Okay, and we just need to draw one correctly. So maybe let us try to draw Q correctly first. Again, let us number the carbon. So this is carbon number 1, 2, 3, 4, 5, and 6. Okay, so I always feel that it's easiest if you simply just draw a chair conformation out first. So I'm just going to draw a chair out first. Okay, and then after that I'm going to number it. 1, 2, 3, 4, 5, and 6. And then after that, you notice that the tertiary butyl group is pointing upwards, so I'll just point it upwards. Okay, and then after that, we go to 2, we go to 3, and then the OH is pointing down. Okay, and then the BR is pointing up, like this. Okay, yeah, so this will be the structure which I will use to explain why the reaction from Q to R occurs rapidly. Okay, so remember we were told that the base will quickly abstract a proton. Okay, so we'll showcase the mechanism here. So we have a base, okay, which will quickly abstract the protons. Okay, and then we'll just showcase deprotonation. And then in the course of deprotonation, I'm going to form the alkoxides. Okay, and then after that, it will be an O minus. Remember to put in your lone pairs of electrons. Okay, and then what do you notice about this? The rear of the CBr bond is actually over here. Okay, can you see? Okay, if I'm going to draw the H, can you see that this is the rear of the CBr bond? Yeah, so this is like a cone, like this. So my O minus will approach from the center of the cone like this. Okay, so the O minus will then approach, and then I will kick out the BR. Okay, so it's a rear attack, and then eventually I'm going to end up with a structure that looks something like this. Oops, sorry. Something like this, and then O, and then like this. Yeah, and that's it. Yeah, so it's a structure that looks a bit weird, seems to be a bit strange, but yeah, it occurs. Okay, the reaction occurs. Okay, before I move on to S and T, right, maybe just let me explain a little bit on what if you started off with the wrong conformation, for example. Because some students will feel that they may not be I mean, some students may argue that, oh, you are able to draw this particular conformation, right? Because you are just lucky, like the first conformation you draw happens to be the correct one. What if I'm not so lucky? Okay, so let me try to answer the what if question. So if let's say you don't start with this chair, for example, maybe you started off with the other chair confirmation like this. Okay, am I still able to get the correct answer? Of course you can, not a problem at all. So let's try. This 1, 2, 3, 4, 5, 6. Okay, so let's say you start off with this where you showcase a super unstable confirmation. Okay, like this. So 1, 2, 3. So in this case, 3 is pointing downwards. So OH is here, and then BR is like that. Okay, if you start with this, you need to do a ring flip. Okay, then maybe let me also showcase or explain one little thing. Whatever you number here, right, must follow your structure. So if I number it anti-clockwise, okay, anti-clockwise, then for my structure, I should also number it anti-clockwise. And then they must point in the correct direction. Okay, do you notice that? So you cannot anyhow draw and then just dump the group in as and when you want, and then feel that I must always put my tertiary butyl group as the equatorial position, no matter what structure I draw. You can't do that. Yeah, so number one is your numbering must follow in the correct direction, either anti-clockwise or clockwise. Number two is they must point in the correct direction. So if it's pointing up, this thing must be pointing up. If it's pointing down, it must be pointing down. If it's pointing up, it must be pointing up. Yeah. So one way to tell one of the quick way to tell, right, whether you are drawing the correct structure is to ask yourself, is my BR and tertiary butyl group in a cis relationship? So these two are cis to each other because they are both pointing up. Then is my BR and OH trans, is my tertiary butyl and OH trans. Yeah. Okay. Yeah. Then from here, I'm going to do a ring flip. Okay, so when I do a ring flip, I will end up with the same structure, right? So this will be like this, and then OH should be here, and then BR will be here. So same structure. Okay, yeah. Then finally, from S to T, why is it slow? So same thought process. So I'm just going to showcase the chair confirmation. Okay, like this. Again, 1, 2, 3, 4, 5, 6. So this is 1, 2, 3, 4, and then this is, oops, the BR is here. Yeah, so this will be the structure. Okay, then in that case, I will need to perform a ring flip. Okay, which is not favorable. Okay, I will need to perform a ring flip in order for me to perform the elimination. Okay, so 1 will be flipped to like this, and then 2, and then 3. 3 will be like this, and then 4. Okay, I will need to perform a ring flip, and then after I perform the ring flip, I will need to do a deprotonation. So I need to deprotonate. So base must deprotonate the H, and then I can do this will then allow me to undergo a direct nucleophilic attack from the rear. Okay, so O minus, lone pair, and then BR. I think I drew this wrongly. This is supposed to be BR here, and then direct SN2. Okay, and then I will end up with the structure for T. Okay, but what is the slow step? This is the slow step. Yeah, because the ring flip is kinetically unfavorable due to the 1,3 diaxial interaction which your tertiary butyl group exert on the rest. Okay, then you might be asking, can we have a SN2 like this? Let's say this particular structure, right? And then my O minus gets abstracted. I mean my H gets abstracted, so I have O minus like this. It's actually a bit hard because the whole structure will become very, very strained. Yeah, because this is a strong base, you will have to undergo some form of a SN2 kind of reaction rate. Then that means that this O minus have to be twisted up a little bit and then attack like that. And this is already in the equatorial position. So when it's twisted, right, you are forcing the whole structure to take on a relatively unfavorable geometry. Okay, then some of you might be asking, what about SN1? Can we have SN1 here? So meaning the bromide leaves, and then can we have SN1 product? Well, I mean, you could, but you need to be aware that our answer is always limited by the flow of the question, because without any experimental data, right, everything you discuss can possibly take place. Yeah. So the question is scoped in such a way that, number one, the first scenario is fast. Okay. The second scenario given to you is slow. So explain it. No need to explain anything beyond, because they didn't even draw the product for you, right? They didn't even showcase to you the SN1 product. Yeah. So in that case, no need to explain extra stuff. And of course, eventually you need to be aware that if it's SN1, right, your tertiary butyl group and your bromide is likely to be in the trans configuration, but in this case, clearly it's not trans. Yeah, so yeah, it's very complicated. So I think every time during exam, right, let's try not to complicate matters by answering things not required by the question. I think that will help a lot. Yep. Okay, so next we'll move on to question 8. Okay, for question 8, part 1, right? You were told that a compound is classified as aromatic if it has 4n plus 2 pi electron. You notice that n is a positive integer, so it can be 1, 2, or 3. Question is, you are supposed to explain how benzene, pyrrole, and pyridine are aromatic. Your answer should indicate double bonds and lone pairs involved. So there is a very specific instructions given to you. Answer should indicate double bonds and lone pairs involved. Okay, so this is actually part of the old syllabus, the old pharmaceutical chemistry syllabus, where the students were taught heterocyclic chemistry, and they learned the Hacker's rule. So the 4n plus 2 pi electrons delocalized in the ring is actually the Hacker's rule. Yeah. However, don't panic. You are not required to study the Hacker's rule at all. If you are taught in school, then that's fine. But you're not required to study Hacker's rule at all. Yeah. As you have seen from the question, whatever you need, whatever information you need is given to you. Yeah. So you don't need to study Hacker's rule. Okay. But I think one thing we need to get established, right, is that benzene, pyrrole, and pyridine, they are all flat. Okay, or meaning planar. Okay, because they are all planar, right? So the carbon and nitrogen, right, they are all sp2 hybridized. I think we need to establish this first. Although we are not exactly answering the question, we have not answered the question yet, but we need to establish these important facts first, like carbon and nitrogen are all sp2 hybridized. Okay, then in that case it's easier if we move on to discuss benzene. Okay, because for benzene, right, you know that it has 3 pi bonds. Okay, and each of the carbon, right, will contribute 1 pi electrons. Yeah, so because each carbon is sp2 hybridized, and there's one unhybridized p orbital containing the electrons. So each carbon contributing 1 electrons. So there are a total of 6 pi electron in benzene. So therefore, in this case, n is equals to 1. Okay, so I think benzene is pretty clear cut. You also learned that in H2. So I think probably requires no further explanation. Okay, for pyrrole, right, it's a little bit interesting because for pyrrole, you have 2 pi bonds over here, and then the n, there's a lone pair. So remember that both pyrrole and pyridine, right, the nitrogen is sp2 hybridized. Okay, so in that case, how shall we decide like the number of electrons being contributed? Well, what we can do is I will draw a structure for you to take a look. So for pyrrole, right, it will probably look something like this in the 3-dimensional view. Okay, and then we have a H here. So you realize that each of the carbon will have a p orbital. Okay, this is not exactly correct, but I'm just going to put a dot here. But technically, it's not correct to put a dot here. But I'm putting a dot here to allow easy count, for us to count easily. So the lone pairs on nitrogen in plural, right, is actually part of the aromatic structure, or rather, it's part of the delocalized electron clouds. Yeah. So in that case, right, we'll be able to tell that each of the carbon contribute 1 pi electrons to the aromatic sextet or aromatic structure, and then the N will contribute 1 lone pair of electrons. Okay, so altogether 6 pi electrons, and N is equals to 1. Okay, so let me repeat. In order for purol to be aromatic in this case, right, the lone pairs of electrons must be part of the aromatic delocalized electron clouds. Okay, the reason is if that is not the case, then there will not be 6 pi electrons around the structures. Yeah. Some of you might argue that, oh, I can have 4. You can't have 4 because N must be an integer. Yeah, so N cannot take on the value of half. Yeah. Okay, for pyridine, it's also a little bit interesting because for pyridine, right, each of the carbon will contribute 1 pi electrons, and then the N also contribute 1 pi electrons. So therefore, the lone pairs of electrons is actually not part of the delocalized structures. Okay, so let me just attempt to draw pyridine out over here. So if we have pyridine, it will look something like this. Okay, like that. Okay, and then the pi electron cloud will be 1, 2, 3, 4, 5. Again, let me do something not really correct. I'll just put in the electrons here for easy counting. Okay, and then the N here, we have a lone electron that is part of the pi bond. Okay, so it will be delocalized. Okay, and then after that, one of the sp2 hybrid orbital on the nitrogen in pyridine, right, where the lone pairs of electrons will reside on it. Yeah. So therefore, the lone pairs of electrons on N in pyridine is orthogonal or perpendicular to the delocalized electron clouds. Okay, so that's how pyridine looks like. So again, 6 pi electron N is equals to 1. Okay, so I hope you don't find this too daunting. And then moving on to part 2, right? You were told that when bromine and iron bromide are used as reagents, benzene undergoes bromination. Okay, so this is H2 stuff. So this is part of what we call electrophilic substitution. Okay, then after that you were told that purol and pyridine undergoes the same type of substitution reaction as benzene. Predict the relative rates of bromination of purol compared to benzene and pyridine compared to benzene, and then you're supposed to explain your reasoning. Okay, so if you take a look at both benzene and purol, right, you realize that benzene is a hexagon, meaning that it contains 6 atoms in the ring. Purol is a pentagon, so there are 5 atoms in the ring. So therefore, for benzene, right, 6 pi electrons over 6 atoms, purol 5 pi electrons over 5 membered rings, I'm sorry, 6 pi electrons over a 5 membered ring. So in that case, the electron density, right, in purol, right, is actually greater than that of benzene. Yeah. So in that case, you would expect the rate of electrophilic substitution to occur faster for purol as compared to benzene. Then you'll be wondering, why is that the case? That is the case because for electrophilic substitution, the rate determining step is the first step involving the pi electron cloud attacking the electrophores. Yeah, so this is very crucial. So the greater the electron density per atom in the ring, you would expect the greater the tendency for the pi electrons to attack the electrophore. So therefore, I expect purol to react faster as compared to benzene. Yeah. What about pyridine? You might be wondering. So in that case, does it mean that pyridine will react the same rates? No, pyridine will react significantly slower because of the electron withdrawing group over here. Okay, so I'm just going to erase this portion. Okay, you realize that pyridine, right, actually has an electron withdrawing Cn over here. Yeah, so this Cn, right, will result in the end being something like electron sink. So the electron density is now withdrawn towards N. So that actually depletes the pi electron cloud of electron densities. By depleting the pi electron cloud of electron density, you are in fact causing a huge activation barrier for the first step of the electrophilic substitution to occur. And then, of course, there are other reasons, and then making things worse, you notice that there's a lone pairs of electrons on nitrogen. So the lone pairs of electrons here actually means that in pyridine, the nitrogen actually acts as a Lewis base, which will make it attract or cause the electrophile to be readily attacked by the pyridinyl nitrogen. Yeah, so in that case, before electrophilic substitution can even take place, right, the N will attack the electrophile. So this is what happens. So I will have the pyridinyl N, okay, attacking the electrophile, resulting in this particular attack with a formal charge here. And this is even worse because now the N is even more electron withdrawing due to the positive formal charge. So now the pyridinyl ring is even less susceptible to electrophilic substitution. Okay, so in that case, in summary, purol react faster as compared to benzene when it comes to electrophilic substitution. Pyridine reacts significantly slower as compared to benzene. Okay, so that's a short response. But of course, to explain the reasoning, then you have to go into some of the details which I've mentioned. Okay, for part 3, you were told that treatment of purol with one equivalent of bromine in the presence of FeBr3 provides compound U as the major product. So this is the major product, and then minor product is this, and then you are supposed to explain this outcome by considering the stability of the cat ionic intermediate involved. Okay, so again, this is pretty important here. Okay, so I think first of all we need to draw up the electrophilic substitution mechanism. Okay, so I will draw up purol. Maybe I should draw from here. So purol. Okay, so you realize that this particular N with the lone pair, right, is what we call the electron source. Okay, so in order for the Br to be substituted at the second position, I must be able to push electron density from the source to the sink. So let me just represent Br with a positive formal charge. Okay, so I push for the source. So this is the source. I push, I push, I push. So this is the sink. Okay, and then eventually I'm going to end up with this particular structure like this. Okay, with a positive formal charge at the nitrogen. Okay, then you will realize, okay, I'm not going to showcase the whole mechanism because it's not required. Okay, so I'm just going to draw this particular carbocation intermediate. Okay, then you realize that when I attempt to draw resonance structures, right, you notice that the positive charge is now spread out amongst a greater number of carbon, or rather atoms in this case. Okay, so just going to showcase the resonance structures drawing. Okay, like this. Okay, like this, and positive charge. Okay, so in that case, I can conclude that the positive charge is now spread out amongst 4 atoms. Okay, so allowing the positive charge to be delocalized, over 4 atoms might be something which you want to consider as part of your answers when you do the comparison by explaining why U is the major product whereas V is the minor product. So now we'll try to look at V here. Okay, so again for V, when we try to draw the electrophilic substitution, okay, so let me just try to draw this out. Okay, I will push. Okay, so I'm going to draw it out like this. Okay, so you notice that for this particular positively charged intermediate, right, the positive charge is only delocalized amongst 2 atoms. Like this. Okay, so when you compare these 2 series of resonance structures, this and this, right, you will notice that for series 1, the positive charge is delocalized over 4 atoms, but for series 2, it is delocalized over 2 atoms. So therefore, the carbon-cationic intermediates leading to U, right, has the positive charge being delocalized over a greater number of atoms, or you can say it's delocalized to a larger extent as compared to the carbon-cationic intermediate leading to minor product V. Yeah, and you would expect the carbocation or the positively charged intermediates leading to U, right, to be more stabilized as compared to the positively charged intermediate leading to V. So because of that, then I expect U to be the major product. Okay, so this is one of the key ideas which you need to mention in your answers. Okay, then next we'll move on to part 4, which actually is quite interesting. So I'll just erase some of these things first. Okay, so for part 4, right, you are required to explain or describe, okay, maybe not explain, just describe the splitting patterns, okay, in the 1H NMR of U and V. Now, this is actually quite difficult stuff because even in for undergraduate level, most of the time, reading NMR for heterocycles, meaning NMR for aromatic structure containing atoms other than carbons, could be quite challenging. Although for the trained pairs of eyes, right, you will be able to determine the splitting pattern. But that is only if you have learned coupling constant well. Yeah, so this is actually a relatively challenging question. But you notice that Cambridge actually, they are quite kind. So they actually say, describe the splitting pattern, ignoring any coupling involving NH of U and V. So basically, your job is actually quite safe in that sense, meaning that not too daunting, because you just need to go back to your fundamentals, or rather the fundamentals you have learned, although they are not 100% correct or 100% complete, I'm not saying 100%, they are not 100% correct. Okay, yeah, so try to go back to what you have learned, the so-called N+1 rule. Okay, in a very simplistic way, although N+1 rule can't really be used in this case, but yeah, just try. Okay, and then you realize that, oh, things are actually not as difficult as it seems. Okay, so let's try. Okay, let's try to utilize whatever we have learned in this and then see whether we can come up with a difference. Okay, so first of all, I think it's helpful if we label the hydrogen. So this HA, HB, and HC. Okay, and then next we'll label this as HD, HE, and HF. Okay, now since we were told that the coupling involving NH is not required, then yeah, in a simplistic way, I would expect HA to be a doublet, am I right? Because it will couple to HB. Okay, so I will expect HA to be a doublet. Okay, and then same thing, I will expect HC to be a doublet as well. Okay, and then for HB, technically, okay, I need to emphasize this. Technically, right, HB should not be a triplet, because some of you will be thinking it should be a triplet, right? So technically, it shouldn't be a triplet. It should be a doublet of doublet, because HA and HC are in a different chemical environment. Okay, so I would expect, but okay, wait. However, right, you were not taught doublet of doublet most of the time. Okay, I mean, depends on the kind of details that your tutors gone through with you in class. Okay, if you just want to use a simplistic n+1 rule and then just conclude as a triplet, I think it should be fine. But if you're a little bit more advanced and you wish to say that it's a doublet or doublet, I think it's fine as well. Yeah, why not? Okay, then what about HF? Okay, I mean, I think my role now is just to just to explain the Barrett's minimum, and then you see whether we can differentiate the two. If we can differentiate, and then that's it. We'll just move on with our life, and then we'll be happy with it. Okay, HF is in isolation, so therefore a singlet. HD, a doublet. Okay, and of course HE is a doublet as well. Yep. And that's it. I think we can differentiate the two, right? Doesn't really matter. Yeah, because in that case, how should we answer part 4? Yeah, well, I mean, we can say that both U and V contains 3 signals. Okay, with a different splitting patterns. Okay, so I would expect U to have 2 doublets and 1 triplet, or you can say 2 doublets and 1 doublet of doublets. And then V to have 2 doublets and 1 singlet. If you wish to do that, you can. Okay, yeah, and then that's how we can differentiate it, and it's fine. Okay, at the university level, if you are a little bit more trained, I mean a little bit more advanced, and you actually study more. I mean, if you wish to, you can read more about it during holidays. You will notice that the chemical shift of heterocycles are quite different from benzene. So they are actually more diluted. I think we can easily understand why, because of the nitrogen. But of course, pyridine and chloride are quite different, and I'll leave you to go and think about why is that the case. Okay, yeah, I'll move on to the next part, which is part B. Okay, so for part B, I think it's a very H2-ish question. You're supposed to explain why bromobenzene does not undergo nucleophilic substitution in water under basic condition. Basically, they're asking you why bromobenzene cannot react with OH minus. Okay, whereas bromocyclohexane reacts readily under nucleophilic substitution under this condition. I think this is pretty straightforward H2 kind of question, because for bromobenzene, the lone pairs of electrons of bromine partially delocalize into the phenol ring, giving it a partial double bond character. Yeah, so therefore the CBr bond is stronger. Yeah, so therefore less reactive, or you can say less readily broken. You can also explain it from the angle that if it's SN2 for a rear attack, the rear of the CBr bond in bromobenzene is not easily accessible as compared to the rear of the CBr bond in bromocyclohexane. Okay, then if you talk about carbocation formation, you can also argue that for bromobenzene, if a carbocation were to be formed, the positive charge will be largely localized in the sp2 hybridized orbital or hybrid orbital, which will not be able to be delocalized into the phenol ring because it is orthogonal to the pi electron count. Whereas for bromocyclobenzene, if it were to undergo SN1, when the Br is lost, then the positive charge, it's kind of like located at largely p orbital, or you can sp3 largely p, or half-half, and then electron donating LQ groups from the two arms can donate electron density to the positively charged carbocation center, and then stabilizing the secondary carbocation. I mean, you can explain. There are a lot of ways to explain this. Yeah, so it depends on what you really want to, how you really want to explain it. And then for B2, compound W can be prepared from bromobenzene, and then in turn X can be prepared from W in a two-step process. Yeah, so the first step is a reaction which you were not taught in H2 and H3, but it came out in A-levels in H2, I think 10 years ago or 8 years ago before. So basically this Grignard reaction, I'm sure, I mean, a lot of the school prelim papers also have said this. Anyway, you're not supposed to comment on the first step. Yeah, you're supposed to discuss W to X. So they ask you to propose a two-step process. Okay, you realize that one of the carbon is missing. You can easily verify this by numbering the carbon. Okay, so you realize that carbon number 2 is missing. Yeah, so for carbon number 2 to be missing and to produce a C-double-bond, you will probably be thinking about oxidative cleavage, okay, of a terminal alkene. So that is something which you should be thinking about. Yeah, so therefore, an easy way to attempt this question is first to perform dehydration, okay, to produce this. So for dehydration, you probably use excess concentrated H2SO4 and then heat. Okay, then after that, you need to perform oxidative cleavage of terminal alkene. So KMnO4 acidified with H2SO4 and then heat. And that's it. Yeah, very straightforward. Okay. Yeah, so you notice that the questions in front is a little bit challenging. Okay, a little bit challenging, and then this is followed by a very H2-ish kind of question for part B. Okay, although it's only 4 marks. And then you end off with something very challenging. In fact, I think for that particular year, I mean for last year, 2020, right? I think a lot of seniors find this question to be relatively challenging. Okay, but if you are again, if your fundamentals in chemical bonding is very strong, actually this question is not that daunting. So let's try to attempt it. By considering the hybridization of the unsaturated carbon centers, draw structures to show the shape of compound Y and Z and how the pi bonds are formed. Deduce if either of these compounds is chiral or exhibits cis trans isomerism. Okay, so again, shouldn't be too daunting as well. Okay, so first of all, I think the easiest way is to determine the formation of the pi bond one by one. So let us try for Y first. So that's one, and label this as carbon 1, 2, and 3. Okay, so let me try to show the stereochemical projection. So for carbon number 1, I will showcase it like this. The reason why I want to showcase stereochemical projection, I'm going to explain to you now, is because I would like to color code the pi bond so that you can see them quite clearly. Okay, now, so first of all, right, the p orbital is orthogonal to the trigonal planar geometry. We need to know that. Okay, so between carbon 1 and 2, this is how the pi bond is being formed by the unhybridized p orbital of carbon 1 and carbon 2. But let us not forget that carbon number 2 is sp hybridized, so it also has an orthogonal p orbital, okay, which will be used to form the pi bond with carbon number 3. Okay, however, for carbon number 3, right, in order for carbon number 3 to overlap with this pi bond, it cannot be in the same plane as this methyl group carbon 1 and H. Okay, so therefore carbon 3, right, must be orthogonal. So therefore it must be on the plane of this computer screen or the board I'm using to write. Maybe I should write the ME out first, it's easier. Okay, are you able to see that? Remember that p orbital, unhybridized p orbital must be orthogonal. So if the p orbital in green is projecting into the plane and out of the plane, then the trigonal planar geometry must be on the plane of the paper. Yeah. If you draw the p orbital as shown in yellow on the plane of the paper, right, then your trigonal planar geometry about C1, right, must be projecting into and out of the plane of the paper. Okay, so therefore the two pi bonds are orthogonal, and because of that, if you just try to sketch out a drawing over here, so let me just try to sketch it out, right? So I'm not going to show the p orbital now. Okay, so I'm just going to showcase a simple drawing like this. Okay, and I try to draw the mirror image. Okay, so let me try to draw the mirror image like this. Okay, you will notice something quite amazing. Okay, so you will notice that the mirror image and itself, right, they are actually non-superimposable. So if you don't believe, please try to draw it out first, like this. Okay, now let us try to superimpose this onto the one on the left. So what are we going to do? We are going to rotate this structure 180 degrees. So which means I'm going to rotate it, I will flip it over with the ME and the H coming out of the plane of the paper, and then after that go back to this. Why do I want to do that? I want to do that because I want to keep this portion consistent or constant, so that I can superimpose onto this. Okay, so maybe I should draw it here. My apologies. I should actually draw it here so that you can see a direct comparison. Okay, so I'm going to draw it here. So H. Okay, you notice that they are on the same plane, right? Same plane also. Same plane. However, right, whatever that is projecting away from you will now be projecting towards you. Whatever that is projecting towards you will now be projecting away from you. Okay, what do you notice about the two? They are not superimposable, right? It is impossible for you to superimpose these two structures. So therefore, these two are they are what we call an enantiomeric pair without a chiral center. Okay, so I repeat, they are an enantiomeric pair without a chiral center. Okay, so we can conclude that Y exhibits enantiomerism. Okay, exhibits enantiomerism, and Y is actually optically active. Okay, would that be alright? Okay, so now we'll do the same thing for Z. Okay, but remember that you need to utilize whatever key terms you have learned in H2. Okay, so remember that you need to be able to use terms like the blue structure and the red structure. They are non-superimposable onto each other. Yeah, so these are the key ideas you need to be able to utilize as part of your answers. Okay, yeah. So now I'm going to draw Z. Okay, so Z, I'm going to use the same logic. Just trying to check out if there's any space, whether there's enough space for me to draw it. Okay, so I'm just going to utilize this little bit of space I have. So again, 1, 2, 3, 4. Okay, so again, I'm just going to draw it a bit smaller. C1. Okay, and then I'm just going to draw the lines C2, C3, C4. Okay, now the same thing. C1, C2, pi 1 like this. Okay, and then C2, C3, pi 1 orthogonal. Okay, remember that C3 is also SP hybridizer, so there's one more here. Okay, like this. Okay, then because of that, now for C4, right, I'm going to have the projection into the plane and then out of the plane. So in that case, the difference between Y and Z is that the terminal group for Y is orthogonal to each other. So I'm referring to this. So this group and this group, they are orthogonal. But for Z, right, the terminal group are on the same plane. Okay. So in that case, are you able to see that Z will exhibit cis-trans isomerism? Because clearly these two are trans to each other. Okay. So therefore, if I draw something like this, this and Z, I call it Z prime. Okay, so I'll call this trans Z and cis Z. Okay, so therefore Z will exhibit cis trans isomerism. Okay, I think a very important realization you need to have when you answer this question, I think I said it a minute ago, is that for Y, the terminal structure, okay, is orthogonal to each other. But for Z, they are on the same plane. And because of that, Y exhibits enantiomerism because mirror image and itself non-superimposable. Z exhibits cis-trans isomerism. Okay, so with that, we have come to the end of the review for the 2020 H3 A-level papers. I hope you find the review beneficial, and if there are any other reviews or things which you will find interesting, or any topics which you want us to conduct or to create a video for it, yeah, please mention it in the comments below so that we know what are the videos which will keep you interested. Thank you.